Hello there and welcome to Life Beyond Scene, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're heading somewhere that looks calm from a distance, but behaves very differently once you're actually there. The Arctic. It's the kind of place people picture as pure and quiet. White snow, blue shadows, a sky so wide it feels like it has room for your thoughts. But scientists, even the ones who love the cold and live for remote fieldwork, still avoid certain areas of it. Not because they don't care, not because they're not brave, but because the Arctic has a way of turning simple plans into complicated problems, and complicated problems into expensive emergencies. Before we ease into the strange reasons behind those avoided places, I want to ask you something gentle and personal. Where are you listening from tonight? And if you happen to know it, what's the temperature outside where you are right now? If you find this kind of slow science soothing, or if you like the feeling of learning something while your mind gradually unwinds, I'd be very grateful if you gave this video a like and maybe subscribed. It helps this quiet little space reach more people who could use a calm moment too. Now, settle in. Let your shoulders drop. Let your thoughts slow down. Because far above the busy world, in a region that looks empty on the map, there are places that even experts treat with caution, and once you understand why, you'll never look at a blank stretch of ice the same way again. Most people talk about the Arctic like it's one single place, one frozen kingdom at the top of the world. But that's a bit like talking about the ocean, as if every part of it is the same. The Arctic is a whole system, made of different seas, different coastlines, different islands, different ice conditions, and different weather patterns. Some areas are relatively accessible. Others are so difficult to work in that even well-funded research teams hesitate, and not because they're afraid of a little cold. One of the first reasons certain areas are avoided is simple, and it's not glamorous. Getting there can be a nightmare. In many parts of the Arctic, there are no roads, there are no towns, there are no fuel stations, there's no quick detour if something goes wrong. The terrain isn't just remote, it's often hostile to the idea of travel itself. You might have to reach a research site by icebreaker ship, which can take days or weeks depending on the ice conditions. Or you might fly in by small aircraft, landing on ice or gravel runways that are only usable in certain seasons. Sometimes the runway is a flat area that someone has checked with radar and a lot of hope. Even once you arrive, the movement doesn't get easier. Snowmobiles can break down, vehicles can get stuck, helicopters can be grounded by fog or wind for days. And wind in the Arctic isn't like wind in a park. It can arrive suddenly, stay for hours, and make visibility drop to almost nothing. When that happens, you can't just push through. You wait, you stay put, you conserve fuel, you protect your equipment, you make sure you don't wander 10 steps away from camp and disappear into the white. So when scientists avoid certain places, it's often because those places are too hard to reach safely, too hard to resupply, and too hard to leave quickly if the situation changes. And the situation can change faster than most people expect. There's a common assumption that the Arctic is slow. Frozen landscapes give that impression. Ice looks still, snow looks settled. It feels like a place where nothing happens quickly. But the truth is, the Arctic can shift in minutes. Weather systems behave differently at high latitudes. The cold air is dense. The pressure gradients can be sharp. Storms can form and move in ways that surprise even experienced forecasters. On top of that, there are fewer weather stations in many Arctic regions, which means fewer measurements feeding into prediction models. Satellites help, but satellites don't replace having real instruments on the ground. That's one reason there are areas where forecasts are less reliable, and when you're planning a field expedition, unreliable forecasts are not a minor inconvenience. They're a serious risk. If you're on sea ice and the wind changes direction, the ice can start moving, not slowly either. Sea ice is not a solid continent. It's a floating surface that drifts, cracks, compresses, and breaks apart. Sometimes it behaves like a sheet. Sometimes it behaves like a pile of broken plates. Sometimes it behaves like a crowded room. where the pressure builds until something suddenly gives. That something can be a lead, which is an opening of water between ice sheets. It can be a pressure ridge, where ice slabs are forced upward into jagged walls. It can be a sudden crack that runs for kilometers. It can be the quiet, unnerving sound of ice shifting under your feet, followed by the realization that the surface you trusted a moment ago is now reorganizing itself. This is one of the big reasons scientists avoid certain ice zones. Not all sea ice is equal. Some is thick, multi-year ice, older and generally more stable, though even that has changed a lot in recent decades. Some is first-year ice, thinner and more vulnerable to breaking up. Some is a patchwork where old ice and new ice meet in complicated boundaries. If you're trying to set up instruments, drill cores, or build a temporary camp, you need stable ice. You need predictable conditions. You need time to work without the ground turning into a moving puzzle. There are places where the ice is simply too dynamic, too fractured, or too unreliable to work on safely. And when researchers say unreliable, they mean something very specific. They mean the ice might look fine from the surface, but it can fail without warning. Thin ice is one problem, hidden water is another. In the Arctic, snow can hide weak spots. It can cover a crack. It can insulate the ice below, changing how it freezes. It can create an illusion of safety. You might see a smooth white surface and assume it's solid, when underneath, the ice is thinner than it should be, or it's layered in a way that makes it weaker, or it's warmed from below by ocean currents. That last part is important. People often imagine the Arctic Ocean as a cold bathtub, but it has currents, and some of them carry relatively warmer water into areas where it can melt ice from below. This is one reason why some areas are especially risky. The ice can look stable, while it's being undermined from underneath like a floorboard with termites. Scientists use tools to assess ice thickness, like ground-penetrating radar and drilling tests, but you can't check every square meter of an area the size of a city. And even if you could, conditions can change between the time you check and the time you return. Then there's the issue of time itself, not in the philosophical sense, in the practical sense. Arctic fieldwork often has narrow windows. If you need stable sea ice, you might only have a few months. If you need open water, you might only have a few weeks. If you need a certain type of snow condition, you might have days. The sun angle matters for visibility. The temperature matters for equipment. The ice conditions matter for travel. Everything matters, and it all changes on schedules you don't control. That leads to another major reason scientists avoid certain areas. Equipment failure. Cold temperatures don't just make people uncomfortable. They change how materials behave. Plastics can become brittle. Metal can contract, lubricants can thicken, batteries lose capacity, electronics can behave unpredictably, screens can freeze, cables can crack. Small problems become big problems when you can't run to a hardware store. If you've ever had your phone battery drop from 40% to 5% just because you stood outside in winter, you've already met the mild version of this issue. Now imagine you're relying on that battery to run a sensor that costs tens of thousands of dollars, or to power a satellite uplink, or to keep a GPS system stable while you're navigating across ice in low visibility. And it's not just batteries, it's everything. Some research requires delicate instruments that must remain calibrated. In the Arctic, vibration from travel can knock things out of alignment. Condensation can freeze inside housings. Ice crystals can clog vents. Salt spray from open water can freeze onto surfaces, building layers that interfere with moving parts. There are regions where these challenges are so persistent that it becomes impractical to deploy certain instruments. You might technically be able to do it, but you'll spend more time troubleshooting than collecting data. You'll risk losing expensive equipment. You'll risk the safety of the team. And for a research project, risk is always weighed against reward. Then there's another kind of risk that most people don't think about, because it doesn't show up in movies as often: communication. In remote Arctic areas, communication can be limited. Satellite phones work, but not always reliably, especially at extreme latitudes depending on satellite coverage and weather conditions. Radio systems have limited range. Internet access can be minimal or non-existent. If something goes wrong, you can't assume you can call for help instantly. Even if you can call, rescue might not be able to reach you quickly. Aircraft might not be able to fly in a storm. Ships might not be able to break through the ice. A medical evacuation might take many hours or days. That changes the entire equation of what safe enough means. A place that might be manageable with quick rescue access becomes far more dangerous when you're essentially on your own for a long time. So scientists choose sites where logistics are at least possible. They choose locations where there's some infrastructure. They choose areas with known routes. They avoid areas where a small incident could become a life-threatening situation simply because help is too far away. And while we're talking about danger, we should talk about wildlife, because the Arctic has animals that do not treat humans as the centre of the story. Polar bears are the obvious example. They are large, intelligent predators that can move quickly and quietly. They can be curious. They can be persistent. They can be difficult to detect until they're close. In many Arctic research camps, bear safety is not an afterthought. It's part of the daily routine. People carry deterrents. They set up perimeter alarms. They keep watch schedules. They store food carefully. They plan travel routes with bear encounters in mind. There are areas where polar bear density is higher, or where bears are more likely to approach humans due to changes in sea ice patterns and food availability. Those areas can become less suitable for certain kinds of research, especially for small teams, and polar bears aren't the only concern. There are walruses that can be aggressive if disturbed. There are musk oxen that can charge. There are wolves in some regions. There are also less dramatic but still serious hazards, like biting insects in summer that can swarm so intensely they interfere with work and cause stress, fatigue, and distraction. Distraction is dangerous in the Arctic, because many hazards don't announce themselves loudly. A snow-covered crack doesn't wave at you, it waits. Now, there's another reason scientists avoid certain areas, and this one is quieter. It's about what's under the ground. Permafrost. Permafrost is ground that stays frozen for at least 2 consecutive years. In some places, it has been frozen for thousands of years. It's not just ice, it's soil, rock, organic material, and frozen water all locked together. Permafrost can be stable when it stays cold, but when it starts to thaw, it can become unpredictable. The surface can slump, it can collapse, it can form sinkholes, it can create landslides, it can change drainage patterns, it can destroy the ground stability that buildings, runways, and equipment rely on. In areas where permafrost is rapidly thawing, working becomes harder. You can't assume the ground will hold. You can't assume a route will remain passable. You can't assume that a spot that was safe last year is safe this year. And permafrost thaw isn't just a structural issue. It can release gases like methane and carbon dioxide as trapped organic material decomposes. That's a major scientific interest, but it also creates practical concerns for fieldwork. Thawing ground can expose old biological material, ancient animal remains, and even microorganisms that have been frozen for long periods. This doesn't mean every thawing site is dangerous in a dramatic way, but it adds layers of complexity, and complexity is exactly what researchers try to minimize when operating far from support. There's also the ocean itself. Some Arctic regions are avoided because the sea conditions are simply too difficult for ships. Icebreakers are powerful, but they're not magic. Thick ice can slow them down. Pressure ridges can block routes. Ice can trap a vessel if conditions shift. There are historical cases of ships being trapped for months. Modern technology reduces risk, but it doesn't erase it. Some seas have especially chaotic ice conditions due to wind patterns and currents. Some coastlines are difficult to approach because of shallow waters, ice-choked bays, or lack of safe anchorage. Some regions have limited charting, meaning the seafloor isn't mapped in enough detail to navigate confidently. And even if you can get a ship in, you still have to operate. Deploying instruments over the side in freezing spray is not simple. Retrieving them can be worse. Working on deck in high winds is dangerous. Equipment can be lost. People can be injured. So when you hear that scientists avoid certain Arctic areas, sometimes it's because the environment makes the cost and risk too high compared to what they can realistically achieve. Then there's a factor that sounds almost like superstition until you see it in action. Magnetism. Near the Arctic, the Earth's magnetic field behaves differently. Compasses can become unreliable. Navigation can be affected. This is especially true near the magnetic pole, where field lines dip steeply. It's not that you can't navigate at all, but you need to rely on systems beyond a simple compass. GPS helps, but GPS can also be affected by space weather. Space weather is real. Solar storms can disrupt communications and navigation signals. In lower latitudes, you might not notice. In the Arctic, it can become a serious operational issue. Researchers working on sensitive measurements, especially those involving electromagnetic instruments, have to account for this. Even basic operations can be complicated if your positioning and communication systems are less stable. And while we're on the topic of things that make the Arctic different, we have to mention light, or the lack of it. In winter, some areas experience polar night, where the sun doesn't rise for weeks or months. In summer, there's the opposite, polar day, where the sun doesn't set. Both conditions affect humans in ways that go beyond inconvenience. Working in constant darkness increases risk. Visibility is reduced. Navigation is harder. Fatigue can be worse. Mental strain increases. Cold feels more intense when there's no sunlight. Simple tasks take longer. Working in constant daylight also has consequences. Sleep can be disrupted. People can lose track of time. Exhaustion builds quietly. And in fieldwork, exhaustion is one of the biggest threats to safety because tired people make mistakes. Some research has to be done in winter darkness. It's valuable. It's necessary. But it requires more support, more planning, and more risk tolerance. That means some areas are avoided during certain seasons, even if they're accessible at other times. Then there are places avoided not because they're physically impossible, but because they are politically complicated. The Arctic is shared by multiple nations. There are territorial claims, there are military interests, there are protected regions, there are indigenous communities whose land rights and priorities must be respected. There are permits required for research. There are restrictions on what equipment can be brought in. There are rules about sampling, drilling, and data sharing. Some areas are avoided because gaining permission is difficult. Some are avoided because the political situation is tense. Some are avoided because research could be misunderstood as surveillance. Some are avoided because it would be unethical to enter without proper collaboration and consultation, and that last point matters. The Arctic is not empty. It has people. It has cultures. It has histories. Scientists who work responsibly understand that the Arctic isn't a blank canvas for experiments. It's home. That means some regions are approached with care, and sometimes the best choice is not to go at all unless the research is truly necessary and properly coordinated. But even beyond politics and ethics, there's another reason certain areas remain avoided. The simple reality that some places are still poorly mapped, poorly measured, and poorly understood. That might sound surprising in a world with satellites and drones and global positioning, but the Arctic is vast and many areas are still data poor. Seafloor mapping is incomplete in some regions. Ice thickness records are patchy. Weather observations are limited. Biological surveys are incomplete. Some areas are avoided because they are unknown in a way that makes planning difficult. It's not fear of the unknown in a dramatic sense. It's the operational problem of unknown conditions. You can't design a safe expedition if you don't know what you're likely to face. And the Arctic is changing quickly. Sea ice patterns are shifting. Ice is thinning in many places. Shipping routes are changing. Storm patterns are changing. Wildlife movements are changing. Permafrost is thawing. Coastal erosion is accelerating. That means old maps and old assumptions can become outdated faster than people expect. A route that was safe a decade ago might now be unreliable. A region that used to have stable ice might now be fractured earlier in the season. A coastline that used to be intact might now be collapsing into the sea. So the avoided areas aren't always the same year after year. Sometimes they move, sometimes they expand, sometimes they shrink. Sometimes a new danger appears, not because the Arctic is angry, but because the system is responding to changes in temperature, wind, and ocean currents. There's a strange irony here. The areas that are hardest to reach are often the ones we most want to study, because they hold answers we can't get elsewhere. Scientists want to measure the thickness of sea ice far from shore. They want to study deep ocean currents under ice. They want to understand methane release from thawing permafrost in remote basins. They want to track how ecosystems shift in regions with minimal human influence. They want to monitor glaciers that are collapsing faster than predicted. But wanting something doesn't make it safe. So what happens instead is that researchers make choices. They choose sites that are accessible enough to reach and leave. They choose areas with existing stations. They choose regions where aircraft can land. They choose coastlines where ships can operate. They choose places where they can get data without gambling lives. This doesn't mean the avoided areas are ignored completely. Some are studied with satellites, some are monitored with drifting buoys, some are sampled with autonomous underwater vehicles, some are visited briefly when conditions allow. But there are still stretches of the Arctic where the combination of unstable ice, unpredictable weather, limited rescue options and high cost creates a strong barrier. Those places remain the ones that experts talk about with a certain tone. Not panic, not drama, just respect. And that respect is earned. Because the Arctic is not a quiet museum of ice. It's a working system, always in motion, always responding, always shifting. It can be calm for days and then suddenly rearrange itself. It can welcome you in and then make it very difficult to leave. Now, if you're listening and thinking, okay, but what are these areas, specifically? The honest answer is that it's not always about a name location you can point to on a tourist map. Sometimes it's a type of place, a kind of ice, a kind of coastline, a certain distance from support, a certain pattern of currents, a certain season, and that's what we're going to do next. We're going to get more specific about the kinds of Arctic zones that scientists approach carefully and why those zones behave the way they do. Because once you understand how the Arctic moves, how it hides danger under simple surfaces, and how it challenges even advanced technology, you start to see the real reason those blank spaces still exist. It's not because humans lack curiosity. It's because the Arctic is one of the few places left that can still say, very clearly, not today. When people say the Arctic, they usually mean one picture in their head. A wide white landscape, a quiet blue horizon, a few slow-moving clouds, maybe a polar bear in the distance. If the imagination is feeling dramatic, it sounds like a single place, a single frozen world. Something you can summarize in one word, like desert, jungle, or ocean. But the Arctic isn't one place at all. It's a whole collection of places that happen to sit under the same general label. And that difference matters, because when scientists avoid certain areas of the Arctic, they aren't avoiding the Arctic as a whole. They're avoiding very specific environments inside it, places that behave differently, places that require different gear, different travel methods, different safety rules, and sometimes different levels of risk. So before we talk about the regions researchers still treat carefully, we need to get something clear. The Arctic is not a single uniform sheet of ice. It's a patchwork, and every patch has its own rules. The simplest way to understand it is to stop thinking of the Arctic as a solid cap on top of the planet, and start thinking of it as a system made of land, sea, ice, weather, and life, all interacting at once. Some parts are mostly ocean covered in drifting ice. Some parts are rocky islands with snow and tundra. Some parts are coastal zones where sea ice forms and breaks every year. Some parts are deep inland where the ground is frozen and the air can be painfully dry. Some parts are shaped by mountains and glaciers. Some parts are flat, open, and exposed to wind from every direction. If you've ever driven across a country and noticed how it changes from city streets to farmland to forest to mountains, you already understand the basic idea. The Arctic is like that, except the distances are larger, the infrastructure is thinner, and the conditions can flip faster than you'd expect. Now, one big reason people think the Arctic is one place is because the word itself is used like a border. You cross into the Arctic Circle, and suddenly it sounds like you've entered a different realm. But the Arctic Circle is just a line of latitude, not a wall. It doesn't mark a sudden change in landscape or temperature. It marks the region where, at least once a year, you can experience a full day of midnight sun and a full day of polar night. That's a useful definition for astronomy. It's not always useful for understanding what scientists deal with on the ground, because in reality, Arctic conditions exist in gradients. They fade in and out. Some places below the Arctic Circle can feel more Arctic than some places above it, depending on the weather, the ocean currents, the altitude, and the season. And season matters in the Arctic more than most people realise. When people imagine the Arctic, they often picture winter, permanent ice, permanent snow, permanent cold. But a large part of the Arctic is not frozen in the same way all year. It goes through intense seasonal shifts. Sea ice grows and shrinks, snowpack builds and melts, rivers freeze and break. Some coastlines become accessible only during short windows. Some routes exist only in winter, when the ground and water are solid enough to travel across. So right away you're dealing with a place that isn't even the same place month to month. Now let's break down what the Arctic actually includes, in a practical sense, because this is where the real complexity begins. There's the Arctic Ocean, which is the central body of water around the North Pole. It's surrounded by the land masses of North America, Europe, and Asia. Unlike Antarctica, which is a continent surrounded by ocean, the Arctic is mostly ocean surrounded by continents. That single fact changes almost everything. An ocean behaves differently than land. It holds heat differently. It moves differently. It creates weather differently. It supports travel differently. It breaks and reforms differently. And when you add ice on top, it becomes even more complicated. The Arctic Ocean is covered by sea ice, but that sea ice isn't a single slab. It's broken into flows, large plates, small plates, thin sheets, thick chunks. It can be smooth in one area and shattered in another. It can be thick enough to support heavy equipment in one region and too thin to trust in the next. Sea ice also drifts. It moves with wind and current. That means the ground beneath your feet might not be the same ground an hour later. It might shift without warning. It might crack. It might compress into ridges. It might open into water. Working on sea ice is closer to working on a moving platform than working on land. It's not impossible. Scientists do it. But it requires a different kind of planning, because you can't treat it as stable terrain. Then you have the coastal Arctic, where the ocean meets land. This is a zone where conditions can be especially unpredictable, because you have the interaction of tides, currents, winds, and land-based weather patterns. Coastal ice forms differently than offshore ice. It can anchor to the shore, it can break away, it can pile up, it can be affected by river runoff, which brings in fresh water and changes how ice forms. Some coastal areas are also shallow, which changes how water moves beneath the ice. Shallow water can warm faster in summer and cool faster in winter. It can also allow ice to ground, meaning it touches the seabed and becomes more stable. Or it can create weird stress patterns where the ice cracks more frequently. From a research standpoint, coastal zones can be attractive because they're easier to access than the deep ocean. You can often reach them from land-based stations. You can travel by snowmobile or small boat depending on the season. You can set up equipment with less logistical burden. But they can also be dangerous because they're transition zones. They're where the system is constantly changing. Shore-fast ice can look solid until it suddenly breaks up. A calm coastline can become a mess of moving ice with very little warning. Then there's the Arctic tundra, the land areas where trees struggle to grow because the ground is cold and the growing season is short. Tundra is not just snowy land. In summer, tundra can be wet. It can be muddy. It can be full of small lakes and bogs. It can swallow vehicles. It can make walking exhausting. In winter, it can be hard-packed and easier to cross, but it can also hide holes, uneven ground, and weak ice over small streams. Tundra also sits on permafrost in many areas. Permafrost is one of the biggest reasons the Arctic behaves differently from other regions. When the ground is frozen year after year, it becomes a foundation. A strange foundation, but a foundation. Roads, buildings, runways, and equipment are built with the assumption that the ground stays stable. But as permafrost warms and thaws, stability disappears. The surface can slump, hillsides can collapse, coastlines can erode faster. What used to be a firm base can become a shifting mess. Scientists studying permafrost often work in places that look harmless. Flat land, a gentle slope, a simple patch of ground. And then they watch it change in ways that surprise even experienced teams. Permafrost zones can be safe to work in with the right planning, but they can also be unpredictable. A site that was accessible one year might be flooded the next. A route that was solid might become a swamp. A storage area might start sinking. Now, add glaciers to the picture. The Arctic includes major ice masses and glaciers, especially in places like Greenland and parts of the Canadian Arctic archipelago, as well as glaciers on Arctic islands and mountainous coastal regions. Glaciers are not static. They flow, they crack, they carve into the sea, they create crevasses that can be hidden under snow. Working near glaciers brings a different set of hazards. Crevasses can be deadly. Weather can change fast. Whiteout conditions can make navigation difficult. The surface can be uneven and unstable. Scientists who work on glaciers often need specialized training and equipment. Ropes, harnesses, ice screws, crevasse rescue skills. It's not casual work. It's not something you do with good boots and confidence. Glaciers are also often in remote areas, which adds logistical challenges. If you're doing research on an ice sheet, you might need aircraft support to reach the site. You might need to land on snow. You might need to transport fuel and supplies. You might need to survive for weeks in an environment where there's no shelter unless you bring it. So when scientists avoid certain Arctic regions, glacier zones can be part of that, especially areas where the terrain is heavily crevassed or where access is too risky. Now let's talk about islands, because the Arctic is full of them. The Canadian Arctic archipelago, for example, is a massive collection of islands. Greenland is an enormous island with its own internal climate and ice dynamics. Svalbard is a group of islands with glaciers, mountains, and polar bear territory. There are Russian Arctic islands. There are Alaskan islands. There are small remote land masses that barely show up on maps. Each island has different geology, different coastline structure, different weather patterns, and different access issues. An island can be a good base for research if it has stable ground and some infrastructure. But it can also be a trap if weather cuts off flights and sea ice blocks ships. In some places, once you're there until nature decides you can leave. And then there are the Arctic seas. The Arctic Ocean isn't a single uniform bowl of water. It includes different seas with different ice behaviour, different currents, and different seasonal patterns. Some areas have more multi-year ice. Some areas are dominated by first-year ice. Some areas are more open water in summer. Some areas are more compressed and ridged. Ocean currents matter because they move heat. They also move nutrients. They shape ecosystems. They affect how ice forms and melts. If you have warmer water moving into a region under the ice, it can melt the ice from below, creating thinner, weaker ice even when the surface looks normal. That's a big deal for travel and for setting up camps or instruments. Some regions have strong currents that create unstable ice edges. Some have frequent formation of leads, open cracks of water. Some have ice that is constantly moving, making it hard to maintain any long-term setup. Now, another thing that makes the Arctic many places is the difference between areas close to human infrastructure and areas that are truly isolated. There are Arctic communities. There are research stations, there are military bases, there are ports, there are airstrips, There are supply routes, but these are scattered. The distance between them can be enormous, and the environment between them can be extremely difficult to cross. If you're working near a station, you might have shelter, communication and emergency support. You might have reliable resupply. You might have a way to evacuate someone quickly if there's a medical issue. If you're working far from infrastructure, everything changes. Every extra kilometre adds risk. Every hour of travel is a cost. Every emergency becomes more serious. This is why scientists don't just choose research sites based on scientific interest. They choose based on practicality. A perfect site that's impossible to support can become a bad site. And this is where the idea of avoided areas begins to make sense. Some areas are avoided because they are too far from support. Some are avoided because they are too difficult to reach. Some are avoided because the terrain is too unpredictable. Some are avoided because the ice is too unstable. Some are avoided because the weather is too hard to forecast. Some are avoided because communication is unreliable. Some are avoided because rescue is not realistically possible in a reasonable time frame. But the Arctic also has another layer of complexity that doesn't get talked about enough. The Arctic is not isolated from the rest of the planet. It's connected to global systems, and those systems influence it. Warm air masses can move north. Storm systems can shift. Ocean currents bring heat. Pollution can travel long distances and end up deposited in Arctic snow and ice. That means Arctic conditions can change not only because of local factors, but because of faraway events. And this matters for researchers because it means the Arctic can be more variable than it used to be. In some places, ice conditions are less predictable year to year. In some places, the timing of freeze-up and break-up is shifting. In some places, storms are stronger or more frequent. In some places, the ice is thinner and more mobile. So when scientists say they avoid certain areas, it's not always because those areas have always been avoided. Sometimes the risk profile has changed. A region that was once manageable might now be too unstable. A route that used to be reliable might now be unpredictable. This leads to a quiet but important truth about Arctic research. A lot of the Arctic that people imagine is based on older ideas, older photos, older expedition stories, older assumptions about thick, stable ice. But the Arctic is not a museum. It's a system that is actively changing. That means scientists have to constantly update how they think about it. They can't rely on tradition. They can't rely on how it used to be. They have to rely on current data. And sometimes current data is incomplete. Now, there's also the human side of this. Because even though we're talking about the Arctic as a physical system, the people who work there are still people. The Arctic affects the body. Cold affects dexterity. Wind affects fatigue. Darkness affects mood. Isolation affects stress. The need for constant alertness wears on you, and different parts of the Arctic affect you differently. A coastal camp might be damp and windy, making cold feel sharper. An inland site might be extremely dry and brutally cold, making breathing feel harsh. A sea ice camp might involve constant subtle motion, cracking sounds, and a sense that the ground is never fully at rest. A glacier site might demand constant attention to footing and route safety. Even when two locations are both Arctic, the experience can be completely different. And for research planning, experience matters. Teams have to choose environments that match their skills and resources. There's also the fact that the Arctic is governed by different rules of light, and light affects everything. In summer there can be continuous daylight. That makes it easier to work in some ways because you have visibility around the clock, but it can also make it harder to rest. People can lose track of time, sleep can become shallow, fatigue can accumulate. In winter, darkness can be constant. That makes travel harder. It makes instrument work harder. It increases the risk of accidents. It can also affect mental health. Not everyone responds well to weeks of darkness, especially under stressful conditions. So some areas might be workable in summer and avoided in winter, or the other way around depending on the research goals. Now let's add one more factor that makes the Arctic many places. The Arctic is not just physical geography, it's also political geography. The Arctic region includes territory and waters connected to multiple countries. Canada, Russia, the United States, Norway, Denmark through Greenland, and others with Arctic interests. That means research access depends on permits, laws, regulations, and international agreements. Some areas might be difficult to enter due to restrictions. Some might be sensitive because of military presence. Some might require local collaboration and community approval. Some might be protected for ecological or cultural reasons. A place can be physically accessible and still effectively off-limits because the permissions are complex or the situation is sensitive. Scientists don't just decide to go somewhere because it looks interesting. They need permission. They need legal clearance. They need to follow ethical guidelines, especially when working near indigenous lands and communities. So in the real world, the Arctic is not one research space. It's many research spaces, each with its own rules. Now, if you take all of this together, the picture becomes clearer. When someone asks, why do scientists avoid certain areas of the Arctic? The first answer is that the Arctic includes areas that are radically different from each other. Some are stable enough for routine work. Some are unstable enough that routine work becomes dangerous. Some are accessible enough to support long-term monitoring. Some are so remote that even reaching them is a major expedition. And in science, especially field science, there's always a balance. The value of the data has to justify the cost and the risk. That balance changes depending on the environment. It changes depending on the season. It changes depending on funding. It changes depending on technology. It changes depending on safety considerations. And that's why some areas are studied heavily while others remain more mysterious. Not because scientists are uninterested, not because the Arctic is too scary, but because some parts of the Arctic are difficult in ways that can't be solved with enthusiasm alone. Now here's the part that's easy to miss. The avoided areas aren't always the same kind of place. They're not all far north. They're not all offshore. They're not all mountainous. They're not all hidden. Some avoided areas are avoided because they're too dynamic. The ice moves too much. The weather shifts too fast. The terrain changes too quickly. Some are avoided because they're too expensive to reach. The cost of transport and support is too high. Some are avoided because they're too risky to work in for long periods. Rescue is too far away. Communication is unreliable. Medical evacuation is not realistic. Some are avoided because the environment breaks equipment too easily. Instruments fail. Power systems struggle. Data collection becomes unreliable. Some are avoided because they're politically or ethically complicated. So when you see an Arctic map and you notice that some regions have lots of data and others don't, it's not because scientists forgot those places exist. It's because those places demand more than most projects can realistically provide. And that leads us into the next idea, which is where this becomes even more interesting. Because there are still parts of the Arctic that remain blank, in the sense that we have fewer measurements, fewer surveys, fewer long-term instruments, fewer direct observations. And the reasons for those blank spots are not mysterious in a supernatural way. They're logistical, they're environmental, they're technical, they're human. So next we're going to talk about those blank spots, what they really mean, and why a blank space on a map can sometimes represent one of the hardest environments on Earth to work in. Not because nothing is there, but because too much is happening at once. When you look at a modern map, it's easy to assume the world is fully known. We have satellites that can photograph a backyard from orbit. We have GPS that can tell you exactly where you are within a few meters. We have drones, radar, sonar, and sensors that can measure things we can't even see. We have computers that can model weather patterns across the planet. We have ships that can cross oceans and aircraft that can reach places once considered unreachable. So when people hear that there are still blank spots on Arctic maps, the reaction is often disbelief. How could there be blank spots left? What do you mean, blank? The truth is, the Arctic still contains areas where our knowledge is thinner than it should be. Not because no one has ever looked, not because the region is hidden, not because it's impossible to detect from space, but because knowing a place in a scientific sense requires more than a picture. A satellite image can show you where ice is. It can show you a coastline. It can show you the rough outline of glaciers and islands. But it can't always tell you how thick the ice is at a specific point. It can't tell you what the water is doing under that ice. It can't tell you what's happening in the sediment on the seafloor. It can't tell you how the chemistry changes from one layer of ocean to another. It can't tell you how stable the ground is in a particular patch of tundra. It can't tell you what's happening during a storm at 2 a.m, when no one is there to measure it. And that's what the blank spots really are. They're not empty areas. They're areas where we have fewer direct measurements, fewer repeated observations, and fewer long-term records. They're gaps in the kind of information scientists need to answer the big questions about how the Arctic works and how it's changing. The Arctic is enormous. It spans millions of square kilometres. It includes ocean basins, continental shelves, island chains, mountain ranges, glaciers, rivers, tundra, and coastlines that stretch for distances most people never really picture. Even if you had perfect technology, you would still have to decide where to focus, because you can't measure everything, everywhere, all the time. So the blank spots begin with a basic limitation. Fieldwork is hard, fieldwork is expensive, fieldwork is slow, and the Arctic makes fieldwork harder than almost anywhere else. To understand why those gaps remain, it helps to picture what scientific data collection actually looks like. Let's say you want to know how the Arctic Ocean is changing. You don't just need one measurement, you need many measurements over time. You need temperature profiles at different depths, you need salinity, you need current speeds, you need dissolved oxygen, you need nutrient levels, you need information about plankton and microbes, you need ice thickness and ice movement, you need wind patterns and atmospheric pressure. You need to know how all of these things interact. One snapshot is not enough. You need time series, you need repeated sampling, you need instruments that can survive in place for months or years. You need data that covers seasons, not just a single expedition. That's where the blank spots become a problem. Because some places are so difficult to access that you can't easily return. And if you can't return, you can't build a long-term record. You might get one set of measurements and then nothing for 5 years. Or you might get data in summer and almost nothing in winter. Or you might get data near the coast and almost nothing offshore. The Arctic, in other words, is not just hard to reach. It's hard to monitor consistently. And consistency is what turns observations into understanding. One major category of blank spot is the deep Arctic Ocean. The central Arctic basin is far from land. It's often covered by sea ice. It can be difficult to reach with ships. Even icebreakers, which are designed for these conditions, have limited time and limited routes. Their operations are expensive. Their schedules are tight. Their missions often combine multiple research goals because the cost of a single expedition is so high. A ship can only be in one place at a time. It can only cover a certain distance. It can only deploy a certain number of instruments. It can only stay as long as fuel and weather allow. So there are large stretches of the Arctic Ocean where measurements are sparse. Not because no one cares, but because getting a ship there is a major project. Then there's the problem of ice itself. Sea ice is not a stable platform. It moves, it cracks, it compresses, it opens into leads of water. It can drift far from where it started. If you deploy instruments on sea ice, those instruments may drift away. If you build a camp on sea ice, the camp may end up in a different place than planned. That makes long-term monitoring difficult. You can deploy drifting buoys, and scientists do. These buoys can measure things like air temperature, pressure, ice motion, and sometimes ocean properties below. But buoys can be lost. They can be crushed by ice ridging. They can fail due to cold and battery issues. They can drift out of the region you wanted to study. So even with modern technology, the data you get can be incomplete. And then there's the simple fact that winter exists. Winter in the Arctic is not just colder summer. It's a different world. There is darkness. There are stronger storms. There is more ice formation. There is less access by ship. There are fewer flights. There are fewer field teams operating. That means winter data is often harder to collect, and many blank spots are blank not because no one ever goes there, but because no one goes there in winter. This creates a bias in our understanding. We know more about summer conditions than winter conditions in many parts of the Arctic. And winter matters. Winter is when sea ice grows. Winter is when the ocean loses heat to the atmosphere. Winter is when certain biological processes slow down or shift. Winter is when storms shape ice and snow. Winter is when the system sets up conditions for the next melt season. If you don't understand winter, you don't fully understand the Arctic. That's one reason blank spots are so frustrating for scientists. The missing data often lines up with the most important processes. Now let's talk about another kind of blank spot, the seafloor. People assume we've mapped the ocean floor in detail because maps look so complete. But large portions of the world's seafloor have not been mapped at high resolution, and in the Arctic, seafloor mapping is even harder. To map the seafloor, you often use sonar from ships. You need to travel back and forth in a grid pattern to build a detailed map. That takes time, it takes fuel, it takes calm enough conditions to operate instruments properly. It requires access. Under ice, it becomes harder. Ships can't always follow perfect survey lines. Ice conditions can force detours. Some areas are inaccessible during certain seasons. Some areas are so remote that survey missions are rare, so there are parts of the Arctic seafloor that remain poorly mapped. That matters because the seafloor shapes ocean currents. It shapes where warm water flows. It shapes where nutrients rise. It shapes ecosystems. It affects how ice behaves indirectly by controlling water movement. If you don't know the seafloor well, your models of ocean circulation can be less accurate. Your predictions can be weaker. Your understanding of heat transport can have gaps. Now, beyond the ocean, there are blank spots on land too. One category is the interior of Greenland. Greenland's ice sheet is enormous. It covers most of the island. Scientists study it intensely because it's a major factor in global sea level rise. But even with that attention, there are areas where data is limited, especially in terms of what's happening at the base of the ice sheet. The surface can be measured with satellites and aircraft. But what's happening deep down, where the ice meets the bedrock, is harder to observe. That interface controls how fast ice flows. It controls how meltwater lubricates the base. It controls how glaciers accelerate toward the sea. To study the base, scientists drill. They use radar. They deploy sensors. But drilling through kilometers of ice is expensive and technically difficult. It requires heavy equipment, fuel, and time. It requires a stable site. It requires a support team. So even in one of the most studied parts of the Arctic, there are gaps. There are places where we don't know the bed conditions in detail. There are places where we don't know exactly how water moves beneath the ice. There are places where we don't know how the geology influences flow. Those gaps matter because small differences at the base can lead to large differences in ice movement over time. Then there's the Canadian Arctic Archipelago, a region full of islands, channels, and narrow waterways. This area is complex. The geography is intricate. Ice conditions vary from channel to channel. Some waterways can be choked with ice even in summer. Some can open unexpectedly. Currents can be strong. Winds can funnel through narrow passages. From a research perspective, this creates both opportunity and difficulty. It's a natural laboratory for studying ice dynamics, ocean mixing, and ecosystem patterns. But it's also a logistical challenge. Moving between islands requires careful planning. Weather can trap teams, ice can block routes, communication can be limited. So there are parts of the archipelago that have less data, especially in winter, and especially in channels that are difficult to access. Now, a blank spot doesn't always mean no data. Sometimes it means not enough data. For example, you might have satellite coverage of sea ice extent, but not enough direct measurements of ice thickness. You might have temperature readings from a few drifting buoys, but not enough to capture variability across a region. You might have coastal weather stations, but nothing in the interior. This is important, because Arctic systems can vary dramatically over short distances. A region that looks similar from above can behave differently depending on local currents, wind patterns, and ice conditions. If you only have a few data points, you might miss that variability. You might assume the whole region behaves like the area you measured, when it doesn't. That's how gaps become misleading. Not because the data is wrong, but because the data is incomplete. Now let's get more specific about why some areas remain hard to measure, even with modern technology. One big reason is that instruments don't like the Arctic. Electronics can fail in cold. Batteries lose power. Moving parts freeze. Ice can crush equipment. Snow can bury sensors. Salt spray can coat surfaces and then freeze into thick layers. If you deploy a sensor in a temperate ocean, you might expect it to last months or years. In the Arctic, you might lose it quickly. It might stop transmitting. It might drift away. It might get destroyed by ice ridging. It might be damaged by storms. This makes long-term monitoring expensive because you have to replace equipment more often. You have to plan for losses. You have to design instruments that can survive extreme conditions. Even then, survival isn't guaranteed. Another reason is that the Arctic is not just cold, it's also isolated. If an instrument fails in a city, you send a technician. If an instrument fails in the Central Arctic Ocean, you might not be able to reach it for months. You might not be able to reach it at all. That means a single failure can create a gap in your data record that lasts a long time. Scientists can build redundancy into systems, but redundancy costs money and adds complexity. And then there's the issue of power. Many instruments need power to operate. In the Arctic, solar power is limited in winter. Wind power can be unreliable or damaging in storms. Batteries lose capacity in cold. Fuel-powered generators require fuel, and fuel requires transport. So powering long-term stations in remote Arctic areas is difficult. That's why many measurements are concentrated near existing infrastructure, where power and maintenance are easier. This creates a pattern where some areas become well studied and others remain sparse. Now there's another kind of blank spot that's less about geography and more about biology. Arctic ecosystems are difficult to study, especially in winter. Marine life under ice is hard to observe. You can't just look down and see what's happening. You need specialized sampling methods. You need underwater cameras, nets, and sensors. You need to work through holes in ice or from submarines and autonomous vehicles. Even then, you're sampling a system that can change quickly. Plankton blooms can appear and disappear. Fish can move. Marine mammals migrate. Microbial communities shift with temperature and nutrient changes. On land, animals move across huge distances. Tracking them requires tags, satellites, and long-term observation. Some species are hard to tag. Some tags fail. Some animals disappear into terrain where signals are lost. So biological blank spots remain, especially in remote regions where field teams rarely go. Now, if all of this sounds like a list of obstacles, it is. But it's also a clue. The Arctic is not blank because it's unknown in principle. It's blank because it's difficult in practice. And that's why certain areas are avoided. Because to fill in a blank spot, you often need to go there. You need to stay there. You need to measure repeatedly. You need to maintain equipment. You need to handle emergencies. You need to support a team. In some Arctic regions, that's manageable. In others, it's a gamble. And the gamble isn't just about human safety. It's also about the scientific value. If you spend millions on an expedition and you lose your instruments to ice, you might return with little usable data. That's not just disappointing. It can set back research programs for years. So scientists prioritize. They focus on areas where they can get reliable data. They focus on places where they can build long-term records. They focus on sites that are representative of broader conditions when possible. But that still leaves gaps, and those gaps matter because the Arctic plays a major role in the global climate system. It influences ocean circulation. It influences atmospheric patterns. It influences sea level through ice sheets and glaciers. It influences ecosystems that support indigenous communities and global biodiversity. If we have blank spots, our models are less accurate. Our predictions are less confident. Our understanding is incomplete. Now, there's a temptation to treat blank spots as mysterious, to imagine hidden secrets, to imagine something strange or forbidden. But the reality is more practical and more interesting in a different way. The blank spots are where the Arctic is hardest to work with. They are where nature has the strongest advantage over our planning. They are where ice moves too much, where weather shifts too fast, where darkness lasts too long, where logistics break down, where instruments fail, where rescue is too far away. In other words, the blank spots often line up with the most challenging conditions. And this is where the story becomes more specific, because not all blank spots are the same kind of blank. Some are blank because they are far offshore under thick ice. Some are blank because they are coastal zones with chaotic ice movement. Some are blank because they are narrow channels that are hard to navigate. Some are blank because they are land areas with unstable permafrost and few access routes. So if you want to understand why scientists avoid certain areas, you have to look at the specific kind of environment that creates the blank spot. And one of the biggest creators of blank spots is something that sounds simple, but isn't. Weather. Arctic weather doesn't just make things uncomfortable. It can stop operations entirely. It can ground aircraft. It can trap ships. It can hide hazards. It can make travel impossible. It can turn a planned day of work into a day of waiting. And waiting in the Arctic is not always peaceful. It can be stressful, because every day you wait is a day you burn fuel, consume supplies, and lose time in your field season. So next, we're going to talk about Arctic weather that behaves like it has its own personality, why it's harder to predict in certain regions, and how it becomes one of the biggest reasons some areas remain out of reach, even when they're right there on the map. In most places, weather is something you check in the background. It's a forecast on a phone, a quick glance before leaving the house, a small decision about whether to bring an umbrella, whether to wear a thicker jacket, whether to leave 5 minutes early. When the forecast is wrong, it's annoying, but it rarely becomes dangerous. You get wet, you get cold, you complain about it later. In the Arctic, weather is not background. It is a controlling force. It decides what you can do, when you can do it, and whether you can do it at all. It can shut down travel, erase visibility, damage equipment, and turn a simple plan into a long wait that burns fuel, time, and energy. And in certain parts of the Arctic, it behaves with a kind of independence that makes even experienced researchers cautious. That's why some areas remain avoided. Not because scientists are unfamiliar with harsh weather, many of them build careers around it. The problem is the way Arctic weather changes, the way it combines with the terrain, and the way it reduces your options when things go wrong. The first thing to understand is that Arctic weather is shaped by a different set of conditions than weather farther south. The sun angle is low for much of the year. The surface is often covered in snow and ice, which reflects sunlight back into space. The air is cold and dense. The ocean is partly insulated by ice in winter and then exposed in summer. The contrast between open water and ice can create sharp local differences in temperature and moisture. All of that affects how clouds form, how winds behave, and how storms move. It also affects forecasting. Forecasting depends on data. Weather models need constant streams of observations from weather stations, balloons, aircraft measurements, ships, and radar. In many Arctic regions, those observations are sparse. There are fewer stations. There are fewer routine flights. There are long distances between measurement points. Even with satellites, there are limits, because satellites do not directly measure every variable in every layer of the atmosphere at all times. That means uncertainty can be higher, and uncertainty in the Arctic is not a small inconvenience. It changes decisions about whether to fly, whether to travel, whether to deploy equipment, and whether to send a team away from shelter. One of the most disruptive Arctic weather conditions is the whiteout. A whiteout is not just bad visibility, it's a loss of the visual cues that tell your brain what the world looks like. The horizon disappears, shadows vanish, depth perception breaks down. The sky and ground blend into one continuous field of pale brightness. In a whiteout, it becomes difficult to judge distance. It becomes hard to tell whether you're walking on flat ground or toward a slope. It becomes hard to see cracks in ice, ridges in snow, or changes in surface texture. Navigation becomes harder, and the risk of walking into a hazard increases sharply. Whiteouts can happen during storms, but they can also happen under overcast skies with blowing snow. That makes them especially frustrating, because a day can look calm and still be unsafe for travel. For field teams, the problem is not only that a whiteout is unpleasant, the problem is that it can trap you. If you are away from camp, you may have to stop moving and wait. If you're operating vehicles, you may have to park and shelter. If you're flying, you may not be able to land, and in the Arctic, a delayed landing is not a mild inconvenience. It can mean rerouting hundreds of kilometers away, or turning back entirely. Whiteouts are one reason certain Arctic regions are avoided for longer work. Areas with frequent flat light and blowing snow create conditions where safe movement is not reliable. Then there is wind, which is one of the most underestimated hazards in the Arctic. Wind does more than make you cold. It changes the surface. It moves snow into drifts that hide holes and cracks. It strips snow away from ridges, exposing hard ice. It pushes sea ice, increasing stress between flows. It can create sudden movement and cracking in the ice pack. It can also make working with hands difficult, because even with gloves, dexterity drops quickly in strong wind and low temperatures. Wind chill is not just a number people mention casually. It represents how fast your body loses heat. In calm air, a temperature might be manageable for a trained team. With strong wind, that same temperature can become dangerous, especially if someone gets wet, if equipment fails, or if a shelter system is compromised. Wind also affects equipment. Sensitive instruments can be shaken, tripods can shift, antennas can vibrate, snow can be driven into vents and seals, cables can whip and crack. A small amount of drifting snow can build up in the wrong place and bury sensors, block air intakes, or freeze moving parts. Some Arctic locations have wind patterns that are more intense than others because of local geography. Mountainous areas can create turbulence. Narrow channels can funnel wind into stronger gusts. Coastal regions can experience sharp wind shifts as air moves between land and sea. A forecast might describe moderate winds, but a specific valley or pass can experience much stronger gusts. That mismatch between broad forecast and local reality is part of what makes Arctic weather feel unpredictable. Storms in the Arctic also behave differently than storms in many other regions. At lower latitudes, storms often move through in a predictable cycle. They arrive, pass over, and move on. In the Arctic, some storms can stall. Pressure systems can linger. A low-pressure system can sit in one place and keep producing wind and snow for days. When that happens, fieldwork stops. If a research team is waiting out a storm, they are still consuming fuel, food, and time. They are still maintaining shelters. They are still monitoring safety. They may be losing the only window they had to complete certain tasks. Arctic research seasons are short. They are limited by daylight, by ice conditions, by shipping schedules, by aircraft availability, and by funding. A week of bad weather can erase a large portion of the workable season. That is one reason scientists avoid certain regions, even if those regions are scientifically important. If weather is frequently disruptive in a specific area, it becomes harder to justify sending teams there, especially if the same data can be collected more reliably somewhere else. Fog is another major problem, especially in coastal areas. Fog forms easily when cold air moves over relatively warmer water, or when moisture increases and temperatures hover near the dew point. In the Arctic, this can happen often in summer and during seasonal transitions. Fog can reduce visibility to almost nothing, and it can persist for long stretches. Fog affects aircraft operations. Many Arctic airstrips are short, remote, and exposed. They rely on good visibility for safe landings. If fog settles in, planes cannot land, helicopters cannot fly safely, resupply stops, evacuation becomes impossible. Fog also affects survey work. A lot of Arctic science relies on aerial mapping, photography and visual observation. Fog cancels those plans immediately. Then there is icing, which is one of the most serious hazards for aviation and for exposed equipment. Icing happens when supercooled water droplets freeze on contact with surfaces. It can build up quickly on aircraft wings and rotors. It can coat antennas, sensors, and structures. It adds weight. It changes aerodynamics. It can cause mechanical failure. Certain temperature ranges, especially near freezing, are more prone to icing. That means the most dangerous icing conditions can occur not in the deepest cold, but in the messy transitional periods when temperatures hover around zero and moisture is present. These are also the periods when sea ice is forming or breaking up, which is already a challenging time for travel. When weather adds icing risk on top of unstable ice, certain areas become much harder to operate in. Another factor that makes Arctic weather feel like it has a mind of its own is the way it interacts with sea ice. Sea ice is not just a surface, it is part of the climate system. It reflects sunlight. It insulates the ocean. It changes how heat moves between water and air. When ice breaks up and open water appears, the ocean absorbs more solar energy and releases more heat into the atmosphere. That can influence local cloud formation and wind patterns. So weather affects ice, and ice affects weather, and the feedback can create rapid changes in local conditions. This is especially true near the marginal ice zone, the shifting boundary where sea ice meets open water. That boundary is one of the most active regions in the Arctic system. It is where storms can churn water, where waves can break ice into smaller pieces, where heat exchange is intense, and where conditions can change quickly. Scientists want to study this zone because it contains important information about how the Arctic is responding to warming. It affects sea ice loss, ocean mixing, and ecosystems. But it is also one of the least stable places to work. The ice edge can move, winds can shift, open water can appear where ice was expected, ice can close in where open water was expected. A ship can find itself dealing with conditions that look different from the plan made days earlier. This instability contributes to the blank spots in Arctic data, because the areas that are most dynamic are often the hardest to sample consistently. Temperature in the Arctic also deserves more attention than the simple phrase, "it's cold." Arctic temperatures can swing quickly, especially in coastal areas. Warm air intrusions can push temperatures upward for short periods. Rain can fall in places where snow was expected. Then temperatures can drop again and refreeze everything. These swings create dangerous surfaces. Meltwater can refreeze into hard, slick ice. Snow layers can change structure. Ice strength can shift. A route that was safe one day can become risky the next. Temperature swings also affect equipment. Freeze-thaw cycles stress materials. They create condensation that can freeze inside housings. They cause expansion and contraction that can loosen fittings and seals. Over time, these cycles increase failure rates. A region that stays consistently cold can sometimes be easier to manage than a region that constantly hovers near freezing, because the near-freezing zone creates the most complicated combination of moisture, ice formation, and instability. Arctic weather also creates psychological strain, which matters more than people expect. Working in extreme cold and wind is exhausting. It takes longer to do simple tasks. Gloves reduce dexterity. Layers restrict movement. Breathing can feel harsh. Every tool used becomes slower. When weather is unpredictable, mental load increases. Teams have to make frequent decisions about whether to continue work, whether to turn back, whether to move equipment, whether to shelter in place. Those decisions are not casual. They affect safety, fuel consumption, and mission success. The constant need to reassess conditions wears people down. Fatigue builds, focus slips, small mistakes become more likely. In an environment where mistakes can be serious, this matters. This is one of the quieter reasons some areas are avoided. A place can be physically possible to work in, but mentally and operationally costly in a way that increases risk over time. Then there is the issue of scale and isolation. A storm in a populated region is disruptive, but there are roads, buildings and services. In the Arctic, there may be none of that. There may be no alternate route. There may be no nearby shelter beyond what you brought. There may be no quick rescue option. When weather closes in, your world shrinks to your tent, your vehicle, or your temporary shelter. You wait, and waiting is not always calm. It can be tense, because you are watching supplies, fuel, and time. Weather also affects communication. Satellite communication can be degraded by heavy precipitation, strong winds, and atmospheric conditions. In some high-latitude regions, coverage can be less reliable, depending on satellite geometry. If weather interferes with communication at the same time it interferes with travel, the situation becomes more serious. Now add the reality that Arctic weather is changing. This is not a vague statement. It has practical consequences for fieldwork. As temperatures rise, some regions experience thinner ice and longer open water seasons. That changes wave activity, because open water allows waves to build. Waves can break up ice faster, creating rougher conditions for ships and ice operations. Some regions experience more frequent rain on snow events. That can create ice layers that affect wildlife and travel. It can also make surfaces more slippery and unpredictable. Storm patterns may shift. The timing of freeze-up and break-up changes. The reliability of historical planning decreases. Scientists who have worked in the Arctic for decades often describe a difference in how predictable conditions feel compared to earlier years. Even if the change is gradual, it matters because Arctic operations depend on narrow margins. A small shift in timing can change whether a route is usable. A small shift in ice strength can change whether a camp is safe. A small increase in storm frequency can reduce the number of workable days. So the weather challenge is not static. It is evolving. All of this is why some Arctic regions remain difficult to study directly, and why certain areas are approached carefully or avoided for routine work. It is not that the weather is always violent. It is that the weather can become limiting without warning, and in the Arctic the consequences of being caught in the wrong conditions are higher. The Arctic does not give many second chances. A delayed flight can become a missed resupply. A missed resupply can become a forced evacuation. A forced evacuation can become impossible if the weather closes in again. This chain of events is not dramatic storytelling. It is a realistic operational concern. So scientists plan for weather in the Arctic with a different mindset. They build flexibility into schedules. They carry extra supplies. They set strict safety thresholds. They choose locations where weather is more manageable, or where access options are more robust, and they avoid places where weather variability is too high for the support available. This leads smoothly into the next piece of the story, because weather is only part of what makes the Arctic difficult. Weather interacts with the surface in ways that create another level of unpredictability. Wind pushes ice, temperature changes weaken it, storms fracture it, fog hides hazards on it. And in many of the avoided areas, the main reason comes down to the ice itself. Not ice as a simple frozen sheet, but ice as something that moves, breaks, rebuilds, and behaves in ways that can surprise people who have never stood on it. So next, the focus shifts to the ice that refuses to stay still, and why that moving surface is one of the strongest reasons some Arctic zones remain out of reach. Ice sounds simple until it isn't. Most people grow up with ice as something small and familiar. A thin sheet on a puddle, a slippery sidewalk, a frozen lake that feels solid and quiet. Even when it's dangerous, it looks straightforward. It's either frozen or it isn't. It either holds your weight or it doesn't. In the Arctic, ice is not a simple surface. It is a moving environment. It shifts, it fractures, it compresses, it drifts, it opens, it closes, and it reshapes itself constantly. It does all of this while looking calm from a distance, and that calm appearance is one of the reasons it catches people off guard. A flat white field can feel stable and permanent, but it might be under stress, sliding past itself or slowly tearing open. This is one of the main reasons scientists still avoid certain Arctic areas. Not because they don't know ice is dangerous, they know. The issue is that in some regions the ice behaves in ways that make long-term work unreliable and sometimes unsafe, even for teams with experience and equipment. The key point is that Arctic sea ice is not land. It is floating. That single fact changes everything. When you stand on sea ice, you're standing on a solid layer that rests on top of ocean water. That layer might be 1 meter thick or several meters thick. It might be young and thin or older and thicker. It might be smooth or broken into pieces. But no matter what it looks like, it is still floating, and it is still part of a moving system. The ocean below it moves. The wind above it pushes it. The ice itself responds by drifting, rotating, colliding, and separating. If you've ever seen slow footage of ice flows moving on a river, you've seen a small version of this. In the Arctic, the scale is much larger, and the forces involved can be enormous. Sea ice can drift kilometers in a day. It can rotate like a giant plate. It can move steadily for hours and then suddenly stop when it hits other ice. Or it can suddenly accelerate when wind shifts. From a scientific standpoint, this movement is fascinating. It tells you about currents, wind patterns, and climate dynamics. From an operational standpoint, it is a constant complication. A camp placed on sea ice is not truly stationary. A line of instruments placed on sea ice will not stay aligned. A route planned across sea ice can change shape. A safe path can become unsafe. In certain regions, the drift is stronger and more chaotic. Those regions are often avoided because the ice cannot be trusted to behave predictably for long enough to complete complex work. Now, when people imagine Arctic ice, they often picture a solid sheet that stretches forever. That image is partly true in some seasons and regions, but even then the sheet is rarely unbroken. Sea ice is made of flows, and flows are separated by cracks and openings that can form and change rapidly. One of the most important features scientists deal with is the lead. A lead is an opening in the ice, often a long, narrow stretch of exposed water. Leads form when ice pulls apart due to wind and current. They can be small, like a few meters wide, or wide enough to look like a river cutting through the ice pack. Leads can open quickly. They can also close quickly. When a lead closes, the ice doesn't gently slide back together like two puzzle pieces. It can crash, pile up, and create jagged pressure ridges. Those ridges can be several meters tall, made of broken slabs forced upward by compression. This means the same area can look completely different within hours. A team might travel across stable ice, return along the same route, and find that a crack has opened across it. Or they might find that a lead has closed and formed a ridge that is now an obstacle. Or they might find thin new ice covering an opening that wasn't there before. That thin new ice is especially dangerous because it can look solid from a distance. In cold conditions, leads can refreeze quickly, forming what looks like a smooth surface. But that new ice can be extremely thin. It can be covered by snow, which hides its true thickness. A person might step onto it and break through. For scientists travelling on ice, thin ice is one of the most serious hazards, because it can appear without obvious warning signs. This is one reason some areas are avoided. Regions with frequent lead formation and closure create unpredictable hazards. They require constant monitoring. They require specialised navigation and safety practices. They increase risk with every movement. Now, another feature of sea ice is the pressure ridge. Pressure ridges form when ice flows collide and compress. The ice can't overlap neatly, so it breaks and stacks, creating ridges above the surface and keels below the surface. These keels can extend several meters underwater. From above, a ridge can look like a low hill or a jagged wall. From below, it can be a thick mass that affects water flow and ice stability. Pressure ridges matter for travel because they create rough terrain. Snowmobiles and sleds can't cross them easily. Vehicles can get stuck. People can slip or injure themselves. In poor visibility, ridges can appear suddenly. Ridges also matter because they indicate stress in the ice pack. Where there are ridges, there is movement, Where there is movement, there are cracks forming elsewhere. So ridges are not just obstacles, they are signals that the ice is active. In some regions, ridging is constant. The ice pack is under continuous compression. Those regions can become chaotic to operate in. Travel becomes slow, routes become unpredictable, equipment transport becomes harder. This makes it difficult to set up research operations that require moving heavy gear across the ice. Now, sea ice also has different types, and those types behave differently. First-year ice forms in a single winter. It is generally thinner and more vulnerable to melting and fracturing. Multi-year ice survives at least one summer melt season and becomes thicker and more compact over time. In the past, the Arctic had a larger proportion of multi-year ice. That ice tended to be thicker and more stable, though it was still dynamic. In recent decades, the proportion of multi-year ice has declined, and first-year ice has become more common in many regions. First-year ice can be easier for ships to break through, but it can be more dangerous for fieldwork because it is thinner and less predictable. It can crack more easily. It can melt faster in summer. It can be weakened by warm water intrusions from below. So in some areas, the shift toward thinner ice has increased risk for operations on the ice. This doesn't mean scientists never work on first-year ice. They do. But it changes the safety margin, and in certain regions where the ice is already under stress, thinner ice can make the difference between manageable and unacceptable. Another complication is snow. Snow on sea ice sounds harmless. It looks soft. It looks stable. But snow changes the ice in several ways. Snow insulates. It reduces heat loss from the ocean to the air, which can slow ice growth. That means thick snow can actually lead to thinner ice underneath. Snow also hides features. Cracks can be covered. Thin ice can be masked. Ridges can be smoothed visually. In flat-like conditions, snow can erase the cues that would otherwise warn you. Snow also creates drift patterns. Wind can pile snow into deep drifts, making travel harder and increasing fatigue. So snow can make the ice more deceptive. That deception is part of why ice in the Arctic can feel alive. It is not just moving, it is disguising itself. It is reshaping itself while hiding the changes. Now, beyond sea ice, there is another kind of moving ice that matters in the Arctic: glacier ice. Glaciers flow downhill under their own weight. They move slowly, but their surfaces can change rapidly because of cracking and melt processes. A glacier surface can contain crevasses, deep cracks that can be hidden under thin snow bridges. These bridges can look solid and then collapse under weight. Scientists working on glaciers use ropes and safety systems because the hazard is not obvious from a distance. A smooth white surface can hide a void that drops tens of meters. In some Arctic regions, glaciers are heavily crevassed and unstable. Those areas are avoided unless the research absolutely requires it and the team has specialized training. But the most common avoided ice zones are sea ice zones, because sea ice is both mobile and widespread. Now, the movement of sea ice isn't random. It follows patterns driven by wind and ocean circulation. One of the most important patterns is the Beaufort Gyre, a large clockwise circulation in the Arctic Ocean north of Alaska and Canada. It collects ice and fresh water and can influence how ice drifts across the region. Another is the transpolar drift, which moves ice from the Siberian side of the Arctic across toward Greenland and out into the North Atlantic. These large-scale drift patterns matter because they influence where ice accumulates, where it thins, and where it breaks apart. For scientists, these patterns create both opportunity and danger. If you deploy a drifting buoy, you might want it to follow a known drift route so it can collect data across a wide region. But if you're working on the ice itself, drift means you are never truly in control of your location. A camp can drift away from its planned evacuation point. A team can drift into an area with more fractured ice. A planned resupply drop can become more complicated because the target location has moved. Drift also affects rescue planning. If someone needs evacuation, you need to know where they are. In a moving ice environment, the location changes constantly. This is one reason some regions are avoided for long-term camps. the risk of being carried into more unstable ice, or farther from support, increases over time. Then there's the sound of ice. People who have never spent time on sea ice often expect silence. Sometimes it is silent, but often it isn't. Sea ice makes noise when it moves. It can crack sharply like a rifle shot. It can groan and grind when floes press together. It can pop and creak as temperature changes cause expansion and contraction. These sounds can be unsettling, but more importantly they are signals. They mean stress is changing. They mean movement is happening. A sudden crack can be harmless if it's small and far away, or it can be a warning that the ice is shifting. In some cases, cracks can propagate quickly, splitting a surface that seems stable. Scientists who work on sea ice learn to listen, but listening does not prevent the ice from changing. It only gives you a chance to respond. Now, consider the practical problem of setting up instruments on ice that moves. If you want to measure ocean temperature, you might drill through the ice and deploy a sensor line. If the ice drifts, that sensor line drifts too. That's fine for some studies, but not for others. If you want to measure ice thickness changes at a fixed location, drift makes it difficult, because your location is moving. If you want to place equipment in a grid pattern, drift will distort the grid. If you want to return to a specific point later, that point may no longer exist in the same form. This is why certain regions are avoided for certain types of experiments. It's not just safety, it's scientific reliability. A research project needs stable conditions long enough to collect meaningful data. If the environment changes too quickly, the experiment becomes harder to interpret. Now, one of the most dangerous situations on sea ice is the combination of movement and invisibility. This happens when ice is changing and visibility is poor. A crack can open during a storm. Snow can blow across it and hide it. Flat light can erase contrast. A person can approach without realizing what's ahead. This is why weather and ice cannot be separated in Arctic risk assessment. They amplify each other. Wind drives ice movement. Temperature affects strength. Storms fracture ice. Fog and whiteout hide hazards. In regions where these factors combine frequently, the ice becomes an environment that is too unpredictable for routine operations. That unpredictability is the real reason the ice feels alive. It is not passive. It responds. It shifts. It reacts to forces above and below it. And it does all of this on a scale that makes human plans feel small. Now, there's another reason scientists avoid certain ice regions, and it's tied to a concept that sounds simple: thickness. Ice thickness is not uniform. Even within a small area, thickness can vary widely. A pressure ridge might contain thick ice blocks stacked together. A nearby lead might have thin, new ice. Snow cover might hide both. This variability means you can't assume that because one spot is thick, the next spot is thick too. Scientists measure thickness using drilling, electromagnetic sensors, radar, and other tools. But you cannot measure every step of a route. You rely on judgment, experience, and cautious travel. In some regions, thickness variability is extreme, especially where ice is constantly breaking and reforming. Those regions are harder to work in safely. Then there is the issue of melt. In summer, sea ice can develop melt ponds, pools of water that form on the surface. Melt ponds absorb sunlight and accelerate melting. They can also hide thin spots and cracks. A melt pond can look like a shallow puddle, but it can be deeper than expected. It can conceal weak ice. It can make travel difficult and wet, which increases cold risk even in summer conditions. Wetness in the Arctic is a serious hazard because wet clothing and cold wind can lead to rapid heat loss. So melt season adds another layer of risk to ice operations. This is why many sea ice research projects are planned carefully around seasonal conditions. Some work is done in late winter or early spring, when ice is thickest and temperatures are stable. Some work is done in summer for specific goals, but summer brings its own hazards. Now, when scientists avoid certain areas, they are often avoiding regions where ice is not just thin, but mechanically unstable. Mechanical instability means the ice is under stress, and likely to fracture or ridge. This can happen near coastlines, near currents, near ice edges, and in areas where wind patterns create constant motion. These are also often the most scientifically interesting areas, because they are where change is happening fastest. But interest does not eliminate risk, so researchers make choices. They may use remote sensing instead of direct presence. They may deploy autonomous instruments rather than camps. They may collect data from ships rather than standing on the ice. They may focus on safer zones and use models to infer what's happening in the more dangerous ones. That is how blank spots remain. Not because no one knows those areas exist, but because working there directly is difficult to justify when ice movement makes the environment unstable. This is also why Arctic research has increasingly relied on autonomous technology. Drifting buoys can collect data without a human standing on the ice. Underwater gliders can move beneath ice and measure water properties. Satellites can track ice movement and extent. Aircraft can survey large areas quickly. These tools help fill gaps, but they do not replace everything. Some measurements still require people. Some sampling still requires drilling and physical collection. Some experiments still require setting up equipment in place. And for those tasks, ice stability matters. So the areas where ice behaves most aggressively, where it fractures and shifts frequently, remain some of the hardest places to work. It is not dramatic, it is practical. A moving surface increases risk, increases cost, increases uncertainty, and reduces the chances of a clean, successful mission. And once ice becomes unreliable, everything built on top of it becomes unreliable too. That leads naturally into the next problem, because even if a team finds stable ice, even if the weather cooperates, there is still a major obstacle that stops many Arctic expeditions before they even begin. Getting there. Not the romantic idea of travelling north, but the real logistical problem of moving people, fuel, food, shelter, and equipment into one of the most remote environments on Earth. So next, the focus shifts from the ice itself to the simple but brutal reality of access, and why some Arctic regions remain out of reach even when they are visible on the map. There are places on Earth that are dangerous because of what happens when you arrive. The Arctic has those places too, but it also has another category. Places that are difficult simply because reaching them is a serious challenge on its own. Not emotionally challenging, not symbolically challenging, logistically challenging. This is one of the most important reasons scientists still avoid certain Arctic areas. Sometimes it has nothing to do with mystery or fear. Sometimes it comes down to a hard practical question. How do you physically get there, and how do you get back? In many parts of the world, access is taken for granted. You drive on roads, you fly into airports, you can buy supplies locally. If you need a replacement part, you can get it shipped. If something breaks, you call someone. If someone gets hurt, an ambulance arrives. In large parts of the Arctic, none of that exists. There are no roads, or there are only short local roads that don't connect to anything beyond the nearest settlement. There are no airports in the usual sense, only small airstrips that may be gravel, ice, or compacted snow. There are no nearby warehouses of spare equipment. There are no quick repairs. There is no casual resupply. The Arctic is not a single empty place, but it contains regions where human infrastructure is thin enough that any expedition becomes a self-contained operation. That means every trip begins long before anyone sets foot on snow or ice. It begins with planning, budgeting, permits, transport arrangements, fuel calculations, equipment lists, emergency planning, and contingency planning for the contingency planning. Because if something goes wrong in a remote Arctic location, there is a strong chance that the team will have to solve the problem with whatever they brought with them, and what they brought with them was limited by what they could carry. That is the core problem of access. The Arctic forces you to think in terms of weight, volume, and time. Every kilogram matters, every litre of fuel matters, every crate of food matters, every piece of shelter matters, every battery matters, every spare part matters. If you forget something, you may not be able to replace it, and if you miscalculate, you may not have enough to finish the mission. Now, there are several ways scientists reach Arctic research sites, and each one comes with limits. One method is by ship. Ships sound like a straightforward solution, because the Arctic has an ocean at its centre. But Arctic shipping is not like shipping in open water. Sea ice changes everything. Even an icebreaker, which is built for these conditions, is limited by the thickness and concentration of ice. It can be slowed down. It can be forced to detour. It can become trapped if conditions shift. It can be prevented from reaching certain regions entirely. And ships are expensive. Operating an icebreaker can cost tens of thousands of dollars per day, sometimes more depending on the vessel and mission. That cost includes fuel, crew, maintenance, logistics, and the opportunity cost of using a rare specialized ship for one project instead of another. So ship-based access is limited by budget and availability. There are also seasonal limits. In many regions, the shipping season is short. Some areas are only accessible for a few months, sometimes only a few weeks, depending on ice conditions. If a project misses its window, it might not happen at all that year. Even when a ship reaches a region, getting from the ship to the exact study site can still be difficult. Sea ice can prevent close approach to shore. Shallow water can prevent safe navigation. Landing equipment may require helicopters, small boats, or over ice travel. So ships provide access, but not simple access. Another method is by aircraft. Aircraft are often the most direct way to reach remote land sites. But Arctic aviation has its own challenges. Many Arctic airstrips are not paved. They may be gravel. They may be ice runways. They may be temporary. Their usability depends on weather, visibility, wind, and surface condition. In winter, ice runways can be stable, but they require careful maintenance and monitoring. In warmer seasons, surfaces can soften, become uneven, or develop melt issues. Small aircraft also have limited payload capacity. They can carry people and some equipment, but heavy cargo becomes a problem. Larger aircraft can carry more, but they need longer, stronger runways and better support infrastructure. Helicopters are useful for short-range transport and site access, especially from ships or base camps. But helicopters are expensive, limited in range, and highly dependent on weather. Fog, wind, and low clouds can ground them. So aircraft provide access, but access that can vanish quickly when conditions change. Another method is overland travel. In some Arctic regions, scientists travel by snowmobile, tracked vehicle, or sled, sometimes pulled by vehicles or even dogs in certain contexts. Overland travel is possible when the surface is stable enough. In winter, frozen ground and sea ice can create routes that don't exist in summer. Rivers become highways, lakes become flat corridors, tundra becomes firm enough to cross. But overland travel is slow, physically demanding and risky. It depends on ice stability, weather, and fuel availability. It requires navigation across featureless terrain where visibility can drop suddenly. Overland travel also has a limit that becomes obvious quickly. Distance. A snowmobile expedition can cover many kilometers, but every kilometer requires fuel, time, and energy. If something breaks, you may have to repair it in the cold. If you can't repair it, you may have to abandon equipment and change plans. Overland routes also depend on seasonal conditions. If the ice is thin, travel becomes unsafe. If snow is too deep, travel becomes exhausting. If storms reduce visibility, travel becomes dangerous. So overland access exists, but it is not a guarantee. Now, one of the biggest reasons certain Arctic areas remain avoided is that they sit beyond the reliable reach of all these methods. Some places are too far offshore for small aircraft support and too ice-choked for ships to reach consistently. Some are in regions where weather makes flying unreliable and ice makes shipping unreliable. Some are in areas where overland travel is impossible because the terrain is broken by open water, unstable ice, or rough geography. These places are not unreachable forever, but they are unreachable reliably, and reliability is what matters for scientific work. A research project needs more than a heroic arrival. It needs repeatability. It needs a way to deliver equipment, maintain operations, and leave safely. This is why access is often the deciding factor in whether a region becomes well studied or remains sparse. Now, access problems don't stop with transport. They extend into everything that transport makes possible. Fuel is one of the biggest limiting factors. In remote Arctic operations, fuel is life. It powers vehicles, it powers generators, it powers heaters, it powers cooking equipment, it powers communication systems, it powers emergency systems. Fuel is heavy, fuel is bulky, fuel is expensive to transport. Fuel can be dangerous to store. Fuel can be lost if containers leak or if extreme cold affects seals. A team cannot bring unlimited fuel, and if they run low, their options shrink quickly. This is one reason some areas are avoided. A remote site might require so much fuel to reach and maintain that it becomes impractical. Even if the science is valuable, the fuel requirement might be too high. Then there is food and water. Food is heavy. It must be calorie dense. It must be stable in cold. It must be enough to cover delays because delays are common. Water can sometimes be melted from snow or ice, but that requires fuel and time. In some places, water sources may be saline or contaminated. In some areas, melting snow is the only option, which adds to the fuel burden. Then there is shelter. In many Arctic field operations, shelter is not a convenience. It is survival. Tents must withstand wind. They must insulate enough to prevent dangerous heat loss. They must be secure on snow or ice. They must be repairable in the field. Some teams use larger modular shelters or insulated huts, but those require transport and setup. The more remote the site, the more robust the shelter needs to be, and the more robust the shelter, the harder it is to transport. So access and shelter become linked. If you cannot transport adequate shelter, you cannot safely stay. Equipment adds another layer. Scientific instruments can be delicate, they can be heavy, they can require power, they can require calibration, they can require spare parts, they can require careful packaging to survive transport. Transport in the Arctic is rough. Equipment can be shaken on sleds. It can be exposed to vibration in aircraft. It can be affected by cold during loading and unloading. It can be damaged by ice and snow. If an instrument breaks in a city, you replace it. If an instrument breaks in a remote Arctic site, you may lose the entire mission. So teams bring redundancy where possible, but redundancy adds weight and volume. Again, access becomes the limiting factor. Now there is also the problem of human support. A field team is not just a group of scientists. It is often a mixed team that includes pilots, mechanics, logistics specialists, safety officers, and sometimes medical support. In remote areas, you might not have all of those roles on site. You might have to rely on a small group doing many jobs. This increases risk because specialized problems require specialized skills. If a vehicle breaks down in extreme cold, you need someone who can fix it. If someone gets injured, you need someone who can stabilize them. If communication fails, you need someone who can troubleshoot. If weather shifts, you need someone who can interpret conditions and make safe decisions. In remote sites, one person might carry several responsibilities. That can work, but it adds stress and increases the chance of errors. Now, beyond the physical difficulty of reaching certain areas, there are also administrative barriers. Access is not only about transport, it is also about permission. Many Arctic regions are governed by strict regulations. Research requires permits. Sample collection requires approval. Certain areas may be protected. Certain activities may be restricted. Some regions require coordination with local communities and indigenous organizations. That coordination is essential for ethical research, and it also takes time and planning. Some regions are sensitive due to military presence or geopolitical issues. Even if a site is physically reachable, it may not be accessible in practice. So access can be blocked by legal and political factors as well as environmental ones. Now, one of the most important access issues is evacuation. In any field operation, planning for emergencies is essential. In the Arctic, it becomes central. If someone becomes seriously ill or injured, evacuation might not be possible immediately. Weather can ground aircraft. Ice can block ships. Darkness can limit operations. Distance can make travel slow. This means teams have to plan for the possibility that they may need to handle emergencies on site for longer than they would in other environments. That affects who can go, what medical supplies are brought, and what level of risk is acceptable. Some areas are avoided simply because evacuation is too uncertain. A site might be scientifically interesting, but if rescue cannot be relied on within a safe time frame, it becomes difficult to justify sending people there. This is not a dramatic decision. It is a responsible one. Because even if a team is highly skilled, the environment can overwhelm planning. Now, access problems also create a subtle scientific effect. They shape where data exists. If researchers can only reach certain areas easily, those areas become well studied. If other areas are difficult, those areas remain sparse. Over time, the Arctic research record becomes uneven. This is not because scientists ignore the hard areas, it is because science depends on repeated observation, and repeated observation depends on access. That is why blank spots persist. Now, there is also a time problem tied to access. Field seasons are short. If you are using a ship, you have limited time before ice conditions change. If you're using aircraft, you have limited time before weather shifts. If you're travelling overland, you have limited time before thaw or storm conditions make routes unsafe. This means many Arctic expeditions operate under pressure. They are not leisurely, they are tightly scheduled. They're constantly balancing safety against productivity. If access becomes delayed, the schedule collapses. A storm at the wrong time can prevent arrival. A delay in shipping can push a project out of its seasonal window. A mechanical failure can force early departure. So access is not just about reaching a place, it is about reaching it at the right time. Some Arctic regions are avoided because their access window is too narrow and too unreliable. Now, the Arctic is full of examples of how access shapes science. There are regions near established research stations where long-term monitoring is strong. There are coastal areas where repeated sampling is possible. There are shipping routes that allow regular oceanographic surveys. Then there are areas far offshore, far from infrastructure, where data is sparse. These are the places that remain difficult, not because humans lack interest, not because technology is weak, but because the combination of distance, weather, ease and limited support creates a barrier that is still very real. So when scientists avoid certain Arctic areas, sometimes the reason is as simple as this. You can't study a place you can't reliably reach, and even if you can reach it once, you may not be able to reach it again. That is why access is one of the most powerful forces shaping Arctic research. It determines where instruments can be maintained. It determines where teams can return. It determines where data accumulates year after year, and it determines whether blank spots remain. Now, once a team does reach a remote Arctic area, there is another problem that often appears quickly. Technology starts to fail. Not in one dramatic moment, but in small ways that pile up. Batteries lose capacity, screens freeze, plastics crack, lubricants thicken, sensors drift out of calibration. The Arctic does not just challenge human travel, it challenges machines, and in the most avoided regions, the environment can break technology faster than teams can repair it. So next, the focus shifts from the problem of getting there to the problem of staying functional once you arrive, and why cold and isolation turn advanced equipment into something surprisingly fragile. Technology is one of the reasons Arctic science is even possible. Without modern equipment, a lot of what scientists know about the far north would still be guesswork. Satellites track ice coverage. Sensors measure temperature and salinity under the ice. GPS provides navigation in a landscape with few landmarks. Radios and satellite phones connect teams to the outside world. Instruments can collect data for months while no human is nearby. But the Arctic has a way of making technology feel less powerful than it does everywhere else. In many environments, technology fails occasionally. In the Arctic, failure can feel like a normal part of the schedule. not because engineers are careless and not because the equipment is poorly made. It fails because the Arctic attacks systems in ways that most devices were never designed to handle for long. This is one of the most practical reasons scientists avoid certain Arctic areas. If a place is remote enough and harsh enough that equipment failure becomes likely, then the cost of working there rises sharply. The risk of losing data rises. The risk of losing expensive instruments rises. The risk of putting people in danger rises. And the Arctic does not usually break technology in one dramatic moment. It breaks it in small, frustrating steps. The first problem is cold. Cold affects almost everything. Metals contract. Plastics become brittle. Rubber stiffens. Seals lose flexibility. Lubricants thicken. Springs behave differently. Cables crack. Screens respond slowly. Buttons become hard to press. Touch screens stop working with gloves. Batteries drain quickly. This sounds like a list of minor annoyances until it happens in a place where you cannot replace parts and cannot easily retreat. A small crack in a cable insulation can become a full failure. A stiffened seal can allow moisture in. A frozen latch can prevent a case from opening. A jammed valve can stop a fuel system. A thickened lubricant can slow a motor until it stalls. Cold turns small weaknesses into big problems. Batteries are the most famous example, because almost everyone has experienced a mild version of it. In cold temperatures, battery chemistry slows down. The battery can still contain energy, but it cannot deliver it efficiently. Voltage drops. Devices shut down unexpectedly. Rechargeable batteries lose capacity. Charging becomes slower and sometimes unsafe if the battery is too cold. In Arctic fieldwork, batteries power almost everything. GPS units, radios, laptops, sensors, cameras, drones, satellite communication systems, headlamps, and scientific instruments. When batteries fail, the entire operation becomes harder. Teams can carry spares, but spares add weight. They can warm batteries inside clothing, but that only helps temporarily. They can use external battery packs, but those also suffer in cold. For long-term instruments left in the field, battery limits can define the entire mission. If a sensor is expected to operate for a year, its power system must survive months of darkness, cold and wind. Solar panels won't help during polar night. Wind turbines can be damaged by storms or icing. Fuel-based generators require fuel and maintenance, which is difficult in remote areas, so power becomes a constant constraint. That is why some areas remain less studied, not because instruments cannot be placed there at all, but because keeping them running reliably is difficult. Then there is the issue of moisture, which sounds strange because people imagine the Arctic as dry. In some regions, Arctic air is dry. In others, especially coastal areas, moisture is common. Snow, fog, frost and sea spray can coat equipment. Moisture can enter housings when equipment is opened for maintenance. Warm breath can condense on cold surfaces instantly. A small amount of water can freeze inside connectors and cause failures. The worst part is that moisture often becomes visible only after it has already caused trouble. A connector might look fine until the inside freezes. A cable might appear intact until ice expands inside it and breaks it. A sensor might read incorrectly because frost formed on a surface it needs to keep clear. Icing is especially destructive. When ice builds up on equipment, it adds weight and changes how things move. It can jam hinges, it can block vents, it can cover solar panels, it can interfere with antennas, it can freeze moving parts solid. If ice forms on a wind turbine, the blades can become unbalanced. If ice forms on a drone, flight becomes dangerous. If ice forms on an antenna, communication quality can drop. In some Arctic regions, icing conditions are frequent enough that maintaining equipment becomes a constant fight. Then there is the problem of vibration and impact. Transport in the Arctic is rough. Equipment is moved by sled, snowmobile, helicopter, aircraft, ship, or human carrying. Every method involves vibration. Every method involves jolts. Every method involves cold. Sensitive instruments can drift out of calibration from vibration. Optical components can misalign. Circuit boards can develop microcracks. Fasteners can loosen. Connectors can work themselves free. If equipment is fragile, it becomes harder to use in remote areas. It needs extra packaging, extra support, extra time to set up. That increases workload and increases the chance of errors. So teams often choose rugged instruments designed for harsh environments, but rugged instruments are often heavier and more expensive. Again, the cost rises. Then there is the problem of software and electronics, which can behave unpredictably in extreme cold. Computers can slow down, displays can freeze or become unreadable, touch interfaces can fail, sensors can produce noisy signals. Electronics can behave differently at low temperatures because component properties change. Even if a device is rated for cold, long exposure can still cause issues. And troubleshooting electronics in the Arctic is not like troubleshooting in a lab. In a lab, you can sit comfortably with tools and manuals. In the Arctic, you might be working with gloves on. You might be working in wind. You might have limited time before fingers go numb. You might be working inside a cramped tent. You might be working with headlamp light. You might be working while trying to keep snow out of your equipment case. This makes every repair harder. Then there is the problem of mechanical systems. Engines behave differently in cold. Fuel can thicken. Diesel can gel. Starting systems struggle. Hydraulic fluids become sluggish. Metal parts contract. Bearings can seize. Vehicles are essential for many Arctic operations. Snowmobiles, tracked vehicles, generators, drilling rigs and pumps. If a vehicle fails, it can strand a team. It can delay work. It can force a change of plans. Mechanical reliability becomes a major factor in site selection. A remote site with no support is less attractive if it requires long travel over difficult terrain, because a breakdown far from camp is a serious situation. Even simple tools can become difficult to use. Plastic handles can crack. Rubber grips stiffen. Adhesives lose effectiveness. Tape becomes brittle. Batteries in power tools fail. Metal tools can become dangerously cold to touch. The Arctic makes basic work slower. Now consider the problem of data. Collecting data is the entire point of the mission. But in the Arctic, data collection can fail in subtle ways. Sensors can drift. Calibration can change. Ice can interfere with measurements. A sensor might be recording, but recording bad data. A camera might be running, but the lens might be frosted. A temperature probe might be measuring its own internal heat instead of the environment. In a laboratory, you can check your data in real time and correct problems. In remote Arctic deployments, instruments might record data internally for months. You may not know something went wrong until you retrieve the instrument, and retrieval might not happen for a long time. That means a single failure can erase an entire season of data. This is one of the reasons scientists avoid certain areas. If the chance of losing data is high, and the cost of reaching the site is high, the mission becomes hard to justify. Then there is communication technology, which is a lifeline in remote work. Satellite phones, satellite internet, radios, GPS. These systems are not perfect anywhere, but the Arctic introduces additional challenges. Satellite coverage at high latitudes can be limited depending on the satellite system. Signal quality can be affected by weather. Antennas can ice up. Power systems can fail. Equipment can be damaged by wind. If communication becomes unreliable, safety planning becomes more complicated. Teams rely on regular check-ins. They rely on the ability to call for help. They rely on the ability to coordinate resupply and evacuation. In a region where communication is consistently difficult, risk increases. Now add the problem of navigation. GPS is extremely useful, but it is not invincible. It depends on signal reception. It depends on functioning receivers. It depends on power. It can be affected by ionospheric disturbances, especially during solar activity. In a landscape with few landmarks, losing GPS can be serious. This is why teams often carry multiple navigation tools and backup systems, but again, backups add weight and complexity. Then there is the problem of time, not the philosophical kind, the operational kind. Arctic fieldwork often runs on a tight schedule. Weather windows are short, transport schedules are strict, daylight conditions matter, ice conditions change. When technology fails, it consumes time. Repairs take longer in cold. Troubleshooting takes longer with limited tools. Waiting for a replacement is often impossible. So technology failure does not just break equipment, it breaks the schedule. A broken sensor might mean you lose a day. A broken generator might mean you lose the ability to recharge batteries. A broken vehicle might mean you lose access to the study site. A broken satellite link might mean you lose coordination with the outside world. These failures stack. That stacking effect is why the Arctic feels so unforgiving to technology. In many places, one failure is manageable. In the Arctic, one failure can trigger others. Power loss affects communication. Communication loss affects safety. Safety concerns force reduced operations. Reduced operations lead to incomplete data. Incomplete data means the mission is less successful, so teams design systems with redundancy, but redundancy has limits. Now there is also the problem of cost. Arctic-grade equipment is expensive, shipping it is expensive, maintaining it is expensive, ensuring it is expensive, losing it is expensive. If a region is likely to destroy instruments, fewer projects can afford to work there regularly. This is one reason some areas remain blank. It is not that they are unknown. It is that they are expensive to study directly. Now technology is improving. Autonomous systems are becoming more capable. Batteries are improving. Satellite networks are expanding. Sensors are becoming smaller and more efficient. But the Arctic remains a harsh environment, and the harshest regions still push technology to its limits. This is why scientists often choose safer areas for direct work and rely on remote sensing and autonomous instruments for the most difficult regions. But even autonomous instruments face the same problems. They still need power. They still need to survive cold. They still need to survive ice movement. They still need to transmit data or store it until retrieval. And retrieval is not guaranteed, so technology does not eliminate the blank spots. It reduces them, but it does not erase them. And this brings the story to another factor that is less obvious but surprisingly important. In some parts of the Arctic, the environment affects not only equipment and weather, but also the magnetic and electrical behaviour of the region. Navigation tools can behave differently. Signals can behave differently. The sky itself can become active in ways that influence communications. This is one of the reasons the far north can feel strange in a practical sense, not mystical, but technical. So next, the focus shifts to magnetic conditions near the top of the world, and why certain Arctic areas introduce complications that do not exist in the same way anywhere else. When people think about the Arctic being difficult, they usually picture the obvious problems: cold, ice, wind, darkness, distance. Those are real, and they shape almost every decision a research team makes. But there is another category of difficulty that doesn't show up in photographs. It doesn't look dramatic. It doesn't announce itself with a storm cloud. It sits quietly in the background until it causes a mistake. Magnetism. Near the top of the world, magnetism becomes less predictable in ways that matter for navigation, communication, and scientific measurements. This is not folklore. It is not a strange rumour from old expeditions. It is a practical issue that engineers and field teams plan around, and in some cases, it is one of the reasons certain areas of the Arctic remain harder to work in than people expect. The Earth has a magnetic field, generated by movement in its liquid outer core. That magnetic field is what makes a compass work. It also shapes the region around the planet known as the magnetosphere, which protects us from much of the charged particle radiation coming from the sun. In most places, the magnetic field is stable enough that you don't think about it. A compass points north. GPS works. Radio signals behave in expected ways. The sky looks normal unless there is a rare solar storm. In the Arctic, the magnetic field is still there, but its geometry and behaviour create complications. The first complication is the difference between true north and magnetic north. True north is the direction toward the geographic North Pole, the point where the Earth's axis of rotation meets the surface. Magnetic north is the direction a compass points, toward the magnetic pole, which is not in the same location and does not stay still over time. In lower latitudes, the difference between true north and magnetic north is often small enough that most people never notice. In high latitudes, the difference can be large and it changes depending on where you are. That difference is called magnetic declination. In the Arctic, declination can be significant, and it can vary sharply across regions. That means a compass can point in a direction that is noticeably different from true north, and if you do not correct for it, your navigation can drift off course. This is not a problem for someone walking in a city. It can be a serious problem for someone travelling across featureless ice or tundra, where there are no landmarks to correct your heading. In a landscape where visibility can drop suddenly, and where a small mistake can lead you away from safety, navigation accuracy matters. Now it gets more complicated. As you move closer to the magnetic pole, compasses become less reliable in a different way. A compass needle aligns with the magnetic field lines. At mid-latitudes, those field lines are angled in a way that makes the needle sit relatively level. Near the poles, the field lines dip steeply downward into the Earth. This is called magnetic inclination or dip. When inclination becomes steep, the compass needle can tilt, drag, and behave poorly. Some compasses are designed to work in certain zones of the world because of this tilt issue. A compass built for one hemisphere or latitude range may not work properly in another. Even with the right equipment, compasses near the pole can become harder to use accurately. The needle may not settle cleanly. It may feel unstable. Small local disturbances can affect it more. So in parts of the Arctic, the simple idea of use a compass becomes less dependable than people assume. This is one reason Arctic navigation relies heavily on GPS and other systems. But GPS is not perfect either. GPS depends on satellite signals travelling through the upper atmosphere. In the Arctic, the upper atmosphere behaves differently because of the interaction between the Earth's magnetic field and charged particles from the Sun. This is where the next category of magnetic weirdness appears. Space weather. Space weather is the term for conditions in space that affect Earth, especially solar activity like solar flares and coronal mass ejections. These events send streams of charged particles toward Earth. When they interact with the magnetosphere, they can disturb the ionosphere, the layer of the atmosphere that reflects and modifies radio signals. The Arctic is one of the regions where these effects are strongest, because the magnetic field lines funnel charged particles toward the polar regions. This is why auroras are common in the Arctic. The aurora is a visible sign of energetic particles colliding with atmospheric gases. It looks beautiful, but it also signals that the upper atmosphere is active. When the ionosphere is disturbed, it can affect communication and navigation signals. High-frequency radio communications can become unreliable. Satellite signals can experience delays and errors. GPS accuracy can degrade. In severe cases, signals can be lost temporarily. In a normal setting, a brief GPS glitch might be annoying. In remote Arctic fieldwork, it can be serious. Teams use GPS for navigation across ice and tundra. They use it to mark routes. They use it to locate cached supplies. They use it to coordinate aircraft landings and resupply drops. They use it to position instruments precisely. If GPS becomes less accurate, those operations become harder. This does not mean GPS fails constantly in the Arctic. It means the risk of disruptions is higher, especially during periods of increased solar activity. For researchers operating in difficult areas, higher risk is enough to change planning. It adds another uncertainty layer to an environment that already has many. Then there is the issue of geomagnetic storms. A geomagnetic storm is a disturbance in the Earth's magnetic field caused by solar activity. These storms can induce electric currents in the ground and in long conductive structures like power lines and pipelines. In populated regions, this can cause power grid problems. In remote Arctic research, the more direct issue is how geomagnetic storms affect instruments. Some scientific instruments are extremely sensitive to electromagnetic conditions. Magnetometers, for example, measure magnetic fields and are used to study Earth's magnetic environment, auroras, and space weather itself. If a team is conducting research that requires stable background magnetic conditions, geomagnetic activity can complicate data interpretation. It can add noise, it can mask subtle signals, it can force researchers to account for disturbances that are not part of their primary target. Even for instruments not designed to measure magnetism, electromagnetic disturbances can influence sensors, communication systems, and power systems in subtle ways. This is one reason certain Arctic locations are chosen carefully for certain experiments. A region with frequent disturbances might be unsuitable for measurements that require quiet electromagnetic conditions. Now, beyond large-scale geomagnetic effects, there is also the issue of local magnetic anomalies. The Earth's crust contains magnetic minerals, and certain geological formations can create localized distortions in the magnetic field. In many places, these anomalies are small enough that they don't matter for everyday navigation. In the Arctic, where compasses are already less reliable due to inclination and declination, local anomalies can add more error. This is especially relevant in regions with complex geology, where iron-rich rocks or certain mineral deposits can distort compass readings. Again, in a city, a small compass error is irrelevant. In a remote region with low visibility and no landmarks, it matters. This is another reason scientists prefer GPS and inertial navigation systems. But those systems depend on power and signal reliability, which can be affected by cold and space weather. So the Arctic creates a situation where no single navigation method is perfect. The solution is redundancy, multiple systems, multiple backups, cross-checking, careful planning. Redundancy works, but it adds weight, cost, and complexity. That matters because access and transport are already difficult. So magnetic issues become part of the broader problem. They add another layer to an environment that already pushes limits. Now there is another magnetic-related issue that affects certain types of research. The Arctic is a key region for studying the magnetosphere, auroras, and space weather interactions. That means some scientists go there specifically because of these conditions, but that also means the environment can interfere with other measurements. For example, certain atmospheric studies require precise measurement of electrical properties. Certain oceanographic studies use instruments that can be affected by electromagnetic noise. Some geophysical surveys rely on stable magnetic backgrounds. If the region is magnetically active, data can be harder to interpret. This doesn't stop research, it just makes it more complicated, and complexity increases cost and time. Now there is a practical aspect that often surprises people: aircraft navigation. Modern aircraft navigation relies on multiple systems, including GPS, inertial navigation, and magnetic heading references. Near the poles, some navigation systems can behave differently because of the convergence of longitude lines and the behavior of magnetic fields. Polar routes require special planning. Certain communication frequencies behave differently. Satellite coverage patterns matter. Navigation calculations change. For research flights in the Arctic, these factors add operational constraints. They can affect where flights can go, how they are planned, and what conditions are acceptable. So magnetic and polar geometry issues don't just affect someone walking on ice. They affect the entire logistics chain. This matters because the hardest to reach Arctic regions are often reached by aircraft support. If navigation and communication are more complex, the cost and risk increase. Now, there is also the human factor. People rely on simple cues when navigating. In a forest, you can follow a trail. In a city, you can follow roads. In the Arctic, especially on sea ice, there may be nothing to follow. When visibility drops, the environment becomes a blank page. In those conditions, navigation tools are not just helpful, they are essential. If those tools become less reliable due to magnetic and atmospheric effects, the margin for error shrinks. That is one reason some areas are avoided for routine work. It is not that navigation is impossible. It is that navigation requires more support and more careful planning. Now, the phrase magnetic weirdness can sound like a joke, but it points to a real operational reality. The Arctic is one of the few places where the Earth's magnetic environment is not just a background feature. It becomes a factor you have to consider actively. It influences compasses, it influences radio signals, it influences GPS reliability, it influences sensitive instruments, it influences aviation operations, and it does so in ways that are not always predictable day to day. Solar activity can change quickly. Geomagnetic conditions can shift. Auroral activity can intensify. The ionosphere can become more turbulent. This is why space weather forecasts exist, and why some Arctic operations pay attention to them the way other operations pay attention to storm forecasts. In the most challenging regions, teams need every advantage. If weather, ice, and logistics are already pushing limits, adding magnetic and signal uncertainty can be enough to change the decision about whether a mission is worth it. So when scientists avoid certain areas of the Arctic, magnetism is rarely the only reason, but it can be one of the reasons that pushes a situation from difficult into too uncertain. Now, the Arctic also introduces another kind of challenge that is less technical and more human, but it is just as real. Light. Not the romantic idea of northern lights, but the practical reality of long periods of darkness and long periods of daylight. The Arctic changes the normal rhythm of day and night, and that changes how people function, how teams work, and how safety is managed. So next, the focus shifts to polar night and polar day, and why the Arctic's strange light cycle becomes another quiet reason certain areas remain difficult to study directly. The Arctic does something to time that most places never do. It stretches it. It compresses it. It removes the normal markers people rely on without thinking. It changes the rhythm of a day until morning and evening stop meaning what they usually mean. This is not a poetic idea. It is a practical reality that affects how scientists work, how they stay safe, and how long they can function effectively in certain regions. At high latitudes, the sun behaves differently. In summer, it may not set for weeks. In winter, it may not rise for weeks. This is polar day and polar night. People often hear those terms and imagine something dramatic. They picture a bright sky that never darkens, or a deep darkness that never ends. That part is true, but what matters more for research is what happens to the human brain when the normal cycle of light and dark disappears. Because the Arctic is not only physically challenging, it is cognitively demanding. It forces people to work in conditions where the environment offers fewer cues, fewer comforts, and fewer opportunities to reset mentally. This is one of the reasons certain Arctic areas are avoided, especially for long operations in winter darkness or in summer, when constant daylight makes rest difficult. The human brain is built around rhythms. One of the most important is the circadian rhythm, the internal clock that helps regulate sleep, wakefulness, body temperature, hormone production, and alertness. This clock is influenced strongly by light. In most places, light changes gradually throughout the day. Morning light tells the brain to wake up. Evening darkness signals the body to prepare for sleep. Even indoors, people often get enough natural light cues to keep the rhythm stable. In polar regions, those cues can disappear. During polar night, there may be no sunrise for weeks or months. During polar day, there may be no sunset. The brain loses one of its strongest signals for timing. This affects sleep. In polar night, people can feel sleepy at unusual times, or they can struggle with insomnia. In polar day, people may feel alert late into the night, because it never looks like night. Even if they are exhausted, the body may not produce the same signals for sleep. Researchers often use blackout curtains, sleep masks, and strict schedules to compensate, but these measures do not fully replace natural cues. Sleep disruption matters in any job. In Arctic fieldwork, it matters more because fatigue is dangerous. Fatigue slows reaction time. It reduces attention. It increases errors. It makes decision-making less reliable. It makes people more likely to take shortcuts. It makes them less likely to notice subtle hazards. In the Arctic, subtle hazards can be serious. A hidden crack in the ice, a drifting snowbank covering a hole, a loose piece of equipment, a change in wind direction, a small sign of weather deterioration. A well-rested person might notice these things quickly. A tired person might miss them. This is one reason polar night and polar day affect safety. Now, beyond sleep, light cycles influence mood. Polar night can contribute to low mood, reduced motivation, and feelings of isolation. Some people experience seasonal affective symptoms when light is limited. Even without clinical depression, long darkness can make days feel heavy. In remote field camps, this effect can be amplified. There may be no social variety, no familiar comforts, and no easy way to change the environment. The work may be repetitive. The weather may trap teams inside shelters for long periods. The darkness may make the world feel smaller. In polar day, the challenge is different. The constant light can create a sense of endlessness. People may work longer without realizing it. They may feel pressure to take advantage of good weather and continuous daylight. Rest can be postponed, and fatigue can build quietly. So both extremes can strain the mind. Now, the Arctic is also a place where light affects perception. In winter darkness, visibility is limited. Headlamps and artificial lights create narrow fields of view. Shadows can be misleading. Depth perception changes. It becomes harder to see texture on snow and ice. In summer, constant daylight can create its own problems. Flat light can reduce contrast. Overcast skies can make the world look uniform. The horizon can blend into the surface, especially over snow and ice. This matters because Arctic terrain often depends on subtle visual cues. A crack in sea ice might be a thin, dark line. A pressure ridge might be a slight rise. A snowdrift might hide a dip. A patch of thin ice might look the same as thick ice when covered by snow. When light is poor, those cues vanish. This increases risk for travel and fieldwork, especially in regions where ice is already unstable. Now, polar night also changes temperature patterns. Without sunlight, the surface cools strongly. Temperatures can drop sharply. Wind chill becomes more severe. Equipment becomes harder to handle. Batteries drain faster. Frost forms more quickly. Cold and darkness together create a more demanding environment than either one alone. This is why winter fieldwork is often limited to well-supported operations, and why some regions are avoided entirely in winter. It is not that scientists cannot work in polar night. They can, and they do. But it requires more infrastructure, more planning, and more tolerance for risk. Some research stations are designed for it. Some missions are built around it. But smaller teams and short projects often avoid it because the cost and difficulty rise steeply. Now, polar night also affects navigation. In darkness, there are fewer landmarks. The sky may not provide useful cues if clouds cover stars. Even when stars are visible, they can be difficult to use for navigation in windy, cold conditions. Artificial lights can help, but they also create a tunnel effect. You see what the light shows you, and you miss what it doesn't. On sea ice, this can be dangerous. Cracks and ridges can appear suddenly in the beam of a headlamp. If a team is moving quickly, reaction time is limited. In polar day, navigation is easier in some ways because visibility can be good around the clock, but the lack of a clear end of day can encourage overwork. Overwork leads to fatigue, and fatigue leads back to risk. Now, the human brain also depends on routine. In normal life, routine is supported by society. Work hours, meal times, social activities, evening rest, sleep. In a remote Arctic camp, routine has to be created intentionally. It has to be enforced, because the environment does not naturally support it. Teams often operate on strict schedules, not because they enjoy discipline, but because discipline prevents exhaustion. In polar day, the temptation is to keep going. The weather is good, the light is good, and there is pressure to collect as much data as possible. In polar night, the temptation can be to sleep too much or lose motivation, especially if weather prevents outdoor work. Both extremes require management. Now, there is another effect of polar light cycles that matters for science itself. Some research depends on light. Visual surveys of wildlife, photography, drone mapping, satellite imagery interpretation, some optical instruments. In polar night, these methods become difficult or impossible without artificial lighting, which can alter behavior in wildlife and interfere with measurements. In polar day, optical methods can work well, but glare from snow and ice can create its own problems. Reflected light can overwhelm sensors. Contrast can be low under certain sky conditions, so the light cycle affects not only human performance, but also the tools available for research. Now, the psychological effects of polar conditions also interact with isolation. In the Arctic, isolation is not just distance from cities, it is distance from normal life. Communication may be limited, internet may be slow, the team may be small, social variety may be minimal, the environment may feel repetitive. In polar night, this can be amplified because the outside world is dark and often hostile. Going outside may require full gear. The cold can make short trips feel like major tasks. In polar day, isolation can feel strange because the environment looks bright and open, but the reality of being far from help remains the same. Both conditions can create stress. Stress affects decision-making, it affects patience, it affects teamwork, it affects attention. In a field setting, teamwork matters. People rely on each other for safety. They rely on each other to catch mistakes. They rely on each other to maintain routine. When the environment strains the brain, small interpersonal issues can grow. Miscommunication becomes more likely. Frustration builds faster. This is not a failure of character. It is a normal human response to a demanding setting. Scientists who work in the Arctic often train not only in technical skills, but also in field psychology. They learn to manage stress, maintain routines, and support each other. But training has limits. Some people adapt well to polar conditions, others struggle. Even the same person can respond differently depending on the mission length, weather conditions, and team dynamics. So when planning expeditions, teams consider not only physical hazards, but also human endurance. This is another reason some areas are avoided. A remote site in polar night may be physically possible, but it may be mentally exhausting in a way that increases risk over time. Now, polar night and polar day also affect something basic: attention. In darkness, the brain has to work harder to interpret the environment. It becomes more alert in some ways, because danger feels closer. But sustained alertness is tiring. Over time, it leads to cognitive fatigue. In constant daylight, the brain can lose the sense of urgency that comes with nighttime. It can feel like there is always time to do more. That can lead to longer work hours and less rest. So both conditions can distort attention in different ways. Now, there is a practical safety issue that connects directly to polar light cycles: emergency response. In darkness, it is harder to locate a person in trouble, it is harder to find equipment, it is harder to land aircraft, it is harder to see hazards. In constant daylight, emergency response is easier in terms of visibility, but fatigue and overwork can increase the chance that an emergency happens in the first place. So the light cycle influences both prevention and response. Now, in some Arctic regions, polar night is not just darkness, it is combined with extreme cold and frequent storms. Those are the regions that become the most difficult for human operations. A team might be able to handle cold, they might be able to handle darkness, they might be able to handle storms. Handling all three at once for weeks is different. This is why some research is concentrated in seasons when conditions are less extreme, even if that means missing important winter processes. Scientists know that winter data is valuable. They know that polar night contains crucial information about sea ice growth, ocean heat loss, and atmospheric dynamics. But collecting that data requires a level of support that not every project can provide, so some regions remain less studied in winter. That creates gaps. Those gaps shape understanding. Now, there is also a strange effect that polar conditions create: time distortion. When there is no sunrise or sunset, days can blur together. The sense of progression weakens. People rely on clocks, schedules, and routines to mark time. This can sound minor, but it affects mental health and motivation. In a long mission, feeling like time is not moving normally can increase stress. It can make people feel trapped, even when the work is going well. This is why experienced teams build structure into their days: regular meals, regular check-ins, regular rest periods, clear work shifts. But again, structure requires discipline, and discipline becomes harder when the environment constantly pressures the team to either do more work or retreat into shelter. So polar night and polar day are not just interesting phenomena. They are operational constraints. They influence how long a team can stay. They influence what kind of work can be done. They influence which regions are practical. And that is why certain areas remain avoided, especially those that combine extreme light cycles with high isolation and high environmental instability. Now, the Arctic has another factor that shapes avoidance decisions, and it is one that people often underestimate because it sounds straightforward. Wildlife. Not wildlife as a tourist attraction, but wildlife as a serious field hazard. Animals that are strong, fast, unpredictable, and sometimes hungry. In some areas, the risk of encountering dangerous wildlife is high enough that it changes how research is done, or whether it is done at all. So next, the focus shifts to Arctic animals that do not need to warn you, and why the presence of wildlife adds another layer of difficulty to certain parts of the far north. The Arctic looks empty in a lot of photos. A wide white horizon, a flat plain of ice, a coastline with no trees, a sky that feels too big for anything to hide in it. That visual emptiness creates a false sense of safety. It makes it easy to believe that the Arctic is quiet, still, and mostly lifeless. In reality, the Arctic is full of life. It's just life that is spread out, adapted to extremes, and often difficult to see until it's close. And some of that life can be dangerous in ways that don't come with dramatic warnings. This is one of the reasons scientists still avoid certain Arctic areas or approach them with strict safety rules. It's not that the Arctic is packed with predators around every corner. It's that when a serious wildlife encounter happens in a remote place, the consequences can escalate quickly. In a city, an emergency is followed by help arriving. In the Arctic, help may be hours away, or days away, or unable to reach you at all because of weather. That changes the meaning of risk. Wildlife risk in the Arctic is not about constant fear. It is about a low-frequency, high-consequence problem. Most days, nothing happens. Then one day, something does. And the animals that cause the most concern are not always the ones people expect, even though one animal dominates the conversation for good reason. The polar bear. Polar bears are not just large, they are built for efficiency. They have powerful muscles, thick fat, dense fur, and the ability to travel long distances over ice and water. They can swim for hours. They can move quickly when they choose to. They have excellent senses, especially smell, which can detect food from far away. In the Arctic, a polar bear is not a rare myth. In many regions, it is a real presence that field teams must plan for every day. The reason polar bears are such a serious concern is not simply that they are predators. It is that they are curious, persistent, and strong enough that normal barriers mean very little. A fence that would stop many animals will not stop a polar bear if the bear is motivated. A storage container that looks solid can be torn open. A tent is not protection. A small shelter is not protection unless it is reinforced. Polar bears also do not always behave in ways that match human expectations. Some animals give clear warning signals before they attack. They display aggression, they vocalize, they posture, they try to scare you away. Polar bears can be different. A bear may approach quietly, it may circle, it may test boundaries, it may come closer, then pause, then come closer again. It may not appear aggressive until it is already too close. This is why scientists and field teams treat bear encounters with extreme seriousness. In some Arctic regions, bear density is higher. In some areas, bears are more likely to approach camps because they associate humans with food, either from past encounters or from the simple fact that human camps smell interesting. This matters because field work often involves food storage, cooking, waste management, and long periods in the same location. A bear that discovers a camp can return. A bear that learns a camp has food can become persistent. And persistence is one of the hardest things to manage, so teams use deterrents. They may set up tripwire alarms around camp. These systems are designed to create noise or signals if something crosses the perimeter. They may use flares. They may carry bear spray where appropriate. In many regions, they also carry firearms as a last resort, because the reality is that in a remote environment, there may be no other way to stop an attack. This is not casual. It requires training, legal permission, and strict rules. The goal is always to avoid harming wildlife, but safety comes first when the threat is immediate. Even with deterrents, the presence of polar bears changes how research is done. People may work in pairs or groups. They may keep constant watch. They may limit how far they travel from camp. They may avoid certain coastlines or ice edges where bears are more likely to appear. In some cases, a research project may be relocated because bears are too active in the area. This is one of the reasons certain regions are avoided. It's not that scientists are unwilling to work there. It's that the cost and risk of constant wildlife vigilance may be too high for the mission. Now, polar bears are the most famous example, but they are not the only wildlife concern. Walruses are another. Walruses are enormous animals, often weighing well over 1,000 kilograms. They have long tusks. They can move surprisingly fast in water and on ice. They can be aggressive if disturbed, especially in groups. Walruses often haul out on ice or shore in large numbers. A research team approaching a haul-out area can create stress in the animals, which can lead to stampedes. Stampedes can injure walruses, and they can also put humans at risk if the animals move suddenly. Walruses are not predators in the same way polar bears are, but their size and behaviour make them dangerous in certain situations. In some regions, walrus haul-outs are common. Those regions may be avoided for certain types of fieldwork, or approached only with careful planning and distance. Then there are Arctic foxes. An Arctic fox is not physically dangerous to an adult human in the way a polar bear is, but it can create problems. Foxes are curious. They can approach camps. They can steal food. They can chew on equipment. They can damage cables and insulation. In a remote camp, losing food or damaging equipment is not a minor inconvenience. It can compromise the mission. Foxes can also carry diseases including rabies in some regions, which adds a health risk. That means even a small animal encounter can become serious if it involves bites or close contact. So teams treat foxes with caution too. Then there are wolves. Wolves exist in some Arctic regions, particularly in parts of North America and Eurasia. Wolves generally avoid humans, but they are capable predators. They can be bold in certain circumstances, especially if food is scarce or if they are habituated to human presence. Wolves are not the primary wildlife concern for most Arctic research teams, but in remote areas, any large predator is treated seriously. Then there are musk oxen. Musk oxen look calm and slow, but they can be aggressive when threatened. They can charge. They have heavy bodies and sharp horns. In certain conditions, they can injure people. Musk oxen are often encountered on tundra and island regions. They are not hunting humans, but they can defend themselves. This matters because field teams may move on foot in areas where musk oxen are present. If an animal feels cornered or stressed, it can react quickly. Now, there are also less obvious wildlife hazards. One is birds. This sounds harmless, but in some Arctic regions, birds nest in large colonies. They can be aggressive in defense of nests. They can dive at people. They can distract workers. They can create noise and stress. More importantly, bird colonies can indicate sensitive ecological areas where human disturbance should be minimized. That can restrict where scientists can work or require special permits and protocols. Another hazard is marine mammals. Seals, for example, use breathing holes in sea ice. They may surface unexpectedly. They may break thin ice. They may create openings that are hidden under snow. A breathing hole is not a wildlife attack, but it is a wildlife-related hazard. A person travelling over ice can encounter a thin area near a hole. Whales can also influence ice behaviour by moving through leads and breaking thin ice, though this is not common in a way that field teams rely on. Still, the presence of marine mammals is part of why sea ice is not a static surface. Now, one of the biggest wildlife-related reasons certain Arctic areas are avoided is the combination of wildlife and isolation. A polar bear encounter near a well-supported research station is still serious, but support exists. There may be trained staff, there may be reinforced buildings, there may be established safety systems. A polar bear encounter on remote sea ice, far from any shelter, is a different situation. In that setting, the team's ability to respond is limited to what they have with them. That increases the stakes. This is why some remote areas are avoided, especially for small teams. The risk of a wildlife encounter is not always higher, but the ability to manage it is lower. Now, there's also the issue of changing Arctic conditions affecting wildlife behaviour. Sea ice loss changes polar bear movement patterns. Bears may spend more time on land. They may travel different routes. They may approach human settlements more often. They may be under greater nutritional stress, which can change behaviour. Walruses may haul out on shore more often when sea ice is less available. That can create larger haul-out groups, which can increase the chance of disturbance and conflict. So wildlife risk is not static. It changes with environmental conditions. This adds another layer of uncertainty to field planning. Now, beyond physical danger, wildlife also creates ethical and legal constraints. Scientists cannot simply move through Arctic environments without considering the impact on animals. Many Arctic species are protected. Disturbing them can be illegal and harmful. Research permits often include strict rules about distance, noise, and interaction with wildlife. Certain areas may be off-limits during breeding seasons. Certain routes may be restricted. So wildlife can limit access not only through danger, but through regulation and responsibility. This matters because some of the most scientifically interesting areas are also biologically sensitive. Coastal zones where animals feed and breed. Ice edges where ecosystems are active. Island regions where bird colonies nest. These areas are valuable for study, but they require careful handling. And careful handling takes time, planning, and resources. Now, there is another hidden effect of wildlife on Arctic research. It changes behaviour. A team working under the possibility of polar bear encounters cannot move freely. They must watch constantly. They must keep equipment close. They must avoid leaving items unattended. They must plan routes with visibility in mind. They must limit distractions. That constant vigilance increases fatigue. Fatigue increases mistakes. So wildlife risk interacts with the other Arctic risks. It adds to the mental load, especially in regions where bears are common. This is why some areas are avoided for longer missions. A short visit might be manageable, a long stay might be too draining. Now, even when wildlife is not directly dangerous, it can still interfere with instruments. Animals can chew cables, they can knock over tripods, they can investigate sensors, they can damage equipment in ways that are not obvious until later. A polar bear can destroy a weather station out of curiosity. A fox can chew through a power line. Birds can perch on instruments and interfere with readings. These problems are not constant. but they happen often enough that Arctic equipment is designed with wildlife in mind. It is often reinforced, elevated or protected with barriers. But barriers are not always effective in remote, harsh environments, so wildlife becomes another factor that shapes where scientists can work reliably. In the end, the Arctic is not empty. It is not lifeless. It is not quiet in the way people imagine. It contains animals that are adapted to survive in extreme conditions, and those animals do not need to warn humans to be dangerous. They are strong, fast, and capable. They belong there. Scientists who enter their environment are guests, and they have to behave like guests. That means respecting wildlife, avoiding unnecessary disturbance, and staying safe. In some regions, that balance is manageable. In others, it becomes too demanding, especially when combined with unstable ice, unpredictable weather, and limited rescue options. That is why wildlife is part of the reason certain Arctic areas remain avoided. And now the story shifts again, because wildlife is a visible risk. You can sometimes see it coming, you can plan for it. But there is another risk that is harder to see. Thin ice, hidden water, sudden collapse. These hazards do not announce themselves, they do not move like animals. They simply exist under the surface, waiting for the wrong step, the wrong moment, or the wrong temperature change. So next, the focus moves to the Arctic hazards that are quiet, hidden, and fast, and why the most dangerous water in the Arctic is often the water you never see until it is too late. Thin ice is one of those hazards that sounds obvious until it becomes personal. Most people know in theory that ice can break. They've seen warning signs near frozen lakes. They've heard stories about someone falling through. They understand the concept, but in the Arctic, thin ice is not always a simple patch you can spot and avoid. It can be hidden under snow. It can form in places that look stable. It can appear overnight. It can sit next to thick ice with no clear boundary. And in some areas, it can be created by forces happening underneath the surface, completely out of sight. This is one of the biggest reasons scientists avoid certain Arctic regions, especially those dominated by unstable sea ice, shifting currents, and frequent cracking. Because falling through ice in the Arctic is not the same as falling through ice near home. The water is colder, the air is colder, the wind is often stronger. The distance to shelter can be large. The ability to dry out and warm up can be limited. Rescue may not be immediate. In that setting, thin ice becomes a serious safety issue, not a minor risk. The first thing that makes Arctic thin ice so dangerous is how difficult it can be to see. Snow covers everything. Snow smooths the surface. Snow hides cracks. Snow hides weak ice. Snow fills in gaps. Snow creates a uniform white blanket that makes the ground look consistent even when it isn't. That uniformity is deceptive. A person travelling over sea ice may be looking at a surface that appears solid and continuous. Underneath, there may be an area where ice is thin because it formed recently, or because it melted from below, or because it is being stretched by ice movement, or because it sits over a current that brings warmer water into the region. In many cases, thin ice is not a visible feature, it is a hidden condition. That means you can't rely on your eyes alone. Scientists and experienced Arctic travellers use tools to detect ice thickness and stability. They drill test holes. They use ground-penetrating radar. They use electromagnetic sensors. They observe surface patterns. They look for subtle signs like changes in snow texture, frost patterns, or the sound of the ice underfoot. But no method is perfect, and in areas where ice is constantly changing, yesterday's measurements may not apply today. That is one reason some regions are avoided. If the ice conditions change too quickly, it becomes impossible to maintain confidence in safe travel routes. Now, there are several ways thin ice forms, and understanding them helps explain why the risk is so persistent. One common cause is new ice over open water. When sea ice cracks or pulls apart, it creates a lead, an opening of water. In cold conditions, that lead can freeze quickly. The surface can look solid within hours or days, especially if snow covers it. But new ice starts thin. It may be only a few centimetres thick at first. It may not support a person. It may support a person briefly and then fail. It may crack under weight. It may bend and break. Snow makes this more dangerous by hiding the difference between old ice and new ice. Old ice might be thick enough to support vehicles. New ice might not support a person. From above, both can look the same. This creates one of the most dangerous situations in Arctic travel. Thin ice disguised as normal terrain. Another cause of thin ice is melt from below. People often imagine ice melting from the top because that's how it works in daily life. Sunlight warms the surface, air temperature rises, snow melts, ice thins. In the Arctic, ice can also melt from below due to ocean heat. The ocean is not uniform. It has layers. It has currents. It has intrusions of warmer water from lower latitudes. It has mixing caused by storms and tides. In some regions, warmer water flows under the ice and melts it from underneath. This can happen even when air temperatures are below freezing. That means the surface can look stable while the underside is being eaten away. This is especially dangerous because surface appearance is not a reliable indicator of strength. A person can walk on ice that looks thick and solid, only to find that it is thinner than expected because the underside has been melted. This is one reason scientists are cautious in regions with strong currents and complex ocean mixing. Those regions can create hidden weak spots. Another cause of thin ice is pressure and stress within the ice pack. Sea ice is not a single sheet. It is a mosaic of flows. These flows move with wind and current. When they move apart, cracks open. When they move together, ridges form. In areas where the ice is constantly being pulled and compressed, the structure becomes complex. Some areas become thick, piled into ridges. Other areas become thin, stretched, and weakened. Cracks can form suddenly and propagate quickly. This creates a patchwork of strong and weak zones. A route across the ice may cross thick stable ice, then thin stretched ice, then thick ridged ice again. The transitions may not be obvious. This patchwork is one reason certain ice zones are avoided for heavy travel or long-term camps. Now, hidden water is not only a problem on sea ice, it can also be a problem on land, especially in tundra and permafrost regions. In summer, tundra can become wet and unstable. The surface layer of soil thaws, creating what is called the active layer. Beneath it, permafrost remains frozen. This creates a strange situation where the top layer can become soft and muddy, while the layer below is solid. Water can pool on the surface because it cannot drain downward through frozen ground. This leads to bogs, ponds, and saturated soil that can look harmless from a distance. Vehicles can get stuck. People can sink into mud. Travel becomes slow and exhausting, but the more dangerous part is what happens when ground collapses. Permafrost thaw can create sudden changes in terrain. When ice-rich permafrost melts, the ground can slump. It can form sinkholes. It can create uneven surfaces. It can collapse beneath weight. This is not always dramatic. Sometimes it is a slow sagging. Sometimes it is a sudden drop. In remote areas, ground collapse can damage equipment, disrupt travel routes, and create hazards that are difficult to predict. Scientists working in permafrost regions often avoid areas where thaw is advanced and terrain stability is poor, especially if heavy equipment is involved. Now, sudden collapse also happens in a different form on ice. Ice can fail suddenly. This is what makes it so dangerous. It doesn't always give warning. A person can be walking on ice that feels solid, and then it breaks. A vehicle can cross a section that holds for a moment and then collapses under stress. A crack can open unexpectedly and widen quickly. This can happen because ice strength is not just about thickness. It is also about temperature, structure, salinity, and internal flaws. Sea ice contains brine pockets and channels, especially in younger ice. These features weaken the ice. They change how it responds to stress. When temperatures rise even slightly, ice can become softer and weaker. When temperatures drop, ice can become more brittle. so the same thickness of ice can behave differently depending on conditions. This makes it hard to rely on simple rules. Now the Arctic adds another complication: distance. In many places, falling through ice is followed by quick rescue and warm shelter nearby. In the Arctic, rescue may be far away. Even if a team is travelling together, pulling someone out of freezing water is only the first step. The next step is preventing hypothermia. Wet clothing in cold wind can cause rapid heat loss. Hands lose dexterity. Zippers become hard to use. Fine motor skills disappear. A person who has fallen into water may be shaking, disoriented, and losing strength. They need dry clothing, warmth, and shelter quickly. In a remote field setting, this requires planning. Teams carry spare clothing in waterproof bags. They carry emergency shelters. They carry stoves. They carry heat packs. They carry communication devices. But in the most remote areas, even good planning has limits. If the weather is bad, setting up shelter can be difficult. If wind is strong, lighting a stove can be challenging. If visibility is poor, moving back to camp can be dangerous. So thin ice is not only about the moment of failure, it is about everything that follows. This is why certain areas are avoided. If an area has a high probability of hidden thin ice, it increases the chance of an incident. If an incident happens, the consequences can be severe. Now, scientists do not avoid thin ice everywhere. They work on sea ice regularly. They travel across frozen terrain, they manage risk, but they choose their sites carefully. They prefer stable ice when possible. They avoid regions with frequent lead formation. They avoid areas with strong currents that create hidden melt. They avoid times of year when ice is rapidly changing. They also use safety practices. Travel in groups, use ropes in certain conditions, carry ice picks, use probes to test ahead, mark safe routes, monitor ice conditions constantly. But even with these practices, there are areas where the risk remains high enough that it changes the decision to go. Now, hidden water also appears in another form: snow-covered openings. A lead can open, then partially refreeze, then be covered by snow. This creates a surface that looks like normal snow, but underneath is thin ice over water. These features can be extremely dangerous because they are invisible. In some cases, a person might notice subtle signs, like a different texture of snow, a slight depression, or a faint line. In poor light, those signs may not be visible. This is why whiteouts and polar darkness amplify thin ice risk. Now, sudden collapse is not limited to sea ice and permafrost. It can also occur on glaciers. Crevasses are deep cracks in glacier ice. They can be hidden by snow bridges. A snow bridge can hold for a while and then fail. Glacier travel requires rope systems and training because the hazard is not visible. Scientists working on glaciers avoid heavily crevassed zones unless necessary. They plan routes carefully. They use ground-penetrating radar in some cases. They rely on experienced guides. Even then, risk remains. So collapse is a broader Arctic theme. Surfaces that look solid can fail. Now, the reason this matters for the bigger story is that thin ice and hidden water create a kind of uncertainty that is hard to tolerate in long-term research. Science requires time. It requires setting up equipment. It requires moving gear. It requires returning to sites repeatedly. It requires building stable routines. In a region where the ground itself can fail without warning, routines become fragile. This is why some areas remain less studied. Not because scientists cannot go there, but because operating there repeatedly is difficult and risky. So thin ice and hidden water contribute to the blank spots. They make some regions too unpredictable for routine fieldwork. They force scientists to rely on remote sensing, autonomous instruments, and occasional brief visits instead of long-term camps. And even those methods have limits, because an autonomous instrument placed in a region with unstable ice can be crushed, lost, or drift away. So the Arctic keeps some of its gaps simply by being unstable. Now there is another layer of difficulty that ties directly into this: the cold itself. Not just the discomfort of cold, but the way deep cold changes materials, changes human physiology, and changes the environment's behaviour. In some avoided areas, the cold is intense enough that it becomes a constant operational barrier. It slows everything down, it breaks equipment faster, it increases risk of frostbite, it turns small mistakes into serious problems. So next, the focus shifts to deep cold that changes everything, and why in some Arctic regions temperature is not just a number, but a force that shapes what is possible. Cold is the most obvious Arctic problem, but it is also one of the most misunderstood. People imagine cold as a simple number on a thermometer, -10, -20, -40. They picture it as discomfort. They picture it as something you solve with a better jacket. In the Arctic, deep cold is not just discomfort. It changes how materials behave, it changes how machines behave, it changes how the human body behaves, it changes how fast mistakes become dangerous, it changes how long tasks take, it changes what is possible, and in certain parts of the Arctic, the cold is intense enough that it becomes a barrier on its own, not because humans cannot survive it, but because operating safely and effectively inside it becomes difficult to sustain. This is one of the reasons scientists still avoid certain Arctic areas, especially in winter and in the coldest inland regions. The first thing deep cold does is remove flexibility from the world. Many materials that feel normal at room temperature become brittle at extreme cold. Plastics crack more easily, rubber stiffens, some metals become more prone to fracture, adhesives lose grip, seals lose elasticity. This matters because Arctic work depends on small components functioning properly. A cracked gasket can let moisture into a housing. Moisture freezes and expands. A connector fails. A sensor stops recording. A communication device loses power. A vehicle struggles to start. In a lab, a small crack is a repair. In the Arctic, a small crack can be a mission failure. Deep cold also changes the behaviour of lubricants. Oil thickens, grease stiffens, hydraulic fluids become sluggish, bearings resist movement, engines have to fight friction that wasn't there before. This affects everything with moving parts. Snowmobiles, generators, drills, pumps, winches, vehicle tracks, even simple hinges and latches. A machine that works fine at -10 can behave very differently at -40. Starting engines becomes harder. Keeping engines running becomes essential. Shutting something down might mean you can't restart it without hours of work and warming procedures. So deep cold creates a constant trade-off between conserving fuel and maintaining functionality. Fuel itself becomes a problem. Diesel can gel in extreme cold. Fuel lines can freeze. Water contamination in fuel can form ice crystals. Filters can clog. Teams use winter-grade fuels, additives, and heating systems to manage this. But the colder it gets, the smaller the margin becomes. This is why some regions are avoided in the coldest periods. It's not that engines cannot run. It's that the system becomes fragile. Now, deep cold also affects batteries even more severely than normal Arctic cold. At extreme low temperatures, battery output drops sharply. Some batteries can stop functioning entirely. Rechargeable batteries lose capacity. Charging becomes inefficient or unsafe. This matters because field operations depend on electricity for navigation, communication, lighting, and instruments. If batteries fail faster than expected, the team must burn more fuel to generate power. That increases fuel consumption. That increases transport burden. That increases risk. So deep cold increases cost and complexity in a direct way. Then there is the human body. The body can survive cold, but it pays a price. The first issue is heat loss. In deep cold, the body loses heat rapidly, especially in wind. Wind strips away the insulating layer of warm air around clothing. Exposed skin cools quickly. Even small gaps in clothing become serious. This is why Arctic clothing systems are layered, and why teams are trained to manage sweat carefully. Sweat is dangerous in deep cold. If you sweat heavily while working, Moisture builds in clothing. When you stop moving, that moisture cools and can freeze. Wet clothing loses insulation. The body cools faster. Hypothermia risk increases. So deep cold forces a constant balancing act. Work hard enough to get the job done, but not so hard that you sweat too much. Move enough to stay warm, but not so much that you overheat. Stop often enough to avoid exhaustion, but not so long that you cool down. This balancing act slows everything down. Simple tasks take longer. Setting up equipment, opening cases, handling tools, writing notes, adjusting straps, securing tents, connecting cables, repairing parts. Hands lose dexterity even with gloves. Thick gloves protect but reduce precision. Thin gloves allow precision but increase frostbite risk. So people switch gloves constantly. They warm hands repeatedly. They work in short bursts. This creates a rhythm that is very different from normal work. Deep cold turns every action into a series of steps. Prepare tools, expose hands briefly, make the adjustment, cover hands again, warm up, repeat. This slows down science. Now, frostbite becomes a constant concern. Frostbite is tissue damage caused by freezing. It can happen quickly in deep cold, especially with wind. Fingers, toes, ears and noses are most vulnerable. Frostbite does not always feel dramatic at first. Numbness can mask danger. Skin can become pale and hard without immediate pain. That means a person might not realise they are being injured until it is already serious. This is why Arctic teams monitor each other. They look for signs on faces. They check hands. They take warming breaks. In remote areas, frostbite is not just an injury. It can end a mission because it reduces a person's ability to function and can require evacuation. Deep cold also affects breathing. In very cold air, breathing can feel harsh. Moisture in breath can freeze on face coverings. Ice can build up around the mouth and nose. The throat can feel irritated. Some people experience coughing or discomfort. This is not usually life-threatening, but it adds to fatigue and discomfort. In deep cold, fatigue accumulates faster. The body burns more energy to maintain heat. Movement in heavy clothing requires more effort. Working in snow and wind is physically demanding, so people tire faster. Tired people make mistakes. This is one of the most direct ways deep cold increases danger. It doesn't have to cause hypothermia or frostbite to be harmful. It can simply push people into exhaustion and poor decisions. Now, deep cold also changes how the environment behaves. Snow becomes different. At warmer temperatures, snow can be soft and sticky. At very cold temperatures, snow can become dry, loose, and powdery. It can blow easily. It can drift into equipment. It can reduce visibility in wind. Ice becomes different too. In extreme cold, ice can become more brittle. Cracks can propagate more sharply. The sound of ice can change. Pressure ridges can form with sharp edges. This matters for travel and safety. Deep cold can also affect sea ice growth. In winter, ice thickens, but growth depends on heat exchange, snow cover, and ocean conditions. In some regions, thick snow insulates the ice and slows growth. In others, open leads freeze quickly, creating thin ice patches that look solid. So deep cold can create a surface that looks uniform but is not uniform. Now, there is another aspect of deep cold that affects science directly: human attention. In extreme cold, the brain focuses on survival tasks: keeping warm, protecting skin, managing clothing, monitoring wind, avoiding sweat. This can crowd out other mental work. A person might be capable of complex analysis in a warm lab. In deep cold, even simple note-taking can feel difficult. Fingers are stiff, pens freeze, screens respond slowly. Time pressure increases. This reduces the quality of field documentation. It increases the chance of missing details. It increases the chance of mislabeling samples or forgetting steps. Teams compensate with checklists, routines, and training, but deep cold still adds friction. Now, consider the effect on instruments again. because instruments don't just fail mechanically. They can also behave differently. Sensors can drift. Electronics can change characteristics. Calibration can shift. Materials contract and alter alignment. Optical systems can fog or frost. Pressure sensors can be affected by ice formation. So deep cold can reduce measurement accuracy, even if nothing breaks. This is why some instruments are kept warm in insulated housings. Some systems use heaters. Some instruments are designed specifically for polar conditions. But heaters require power, and power requires fuel or batteries, and deep cold reduces battery performance. So the cold creates a loop. Cold reduces power efficiency. Reduced power makes heating harder. Less heating increases cold exposure for instruments. More exposure increases failures. This is one reason certain regions remain avoided for long deployments. Keeping equipment alive for months in extreme cold is difficult, especially without regular maintenance. Now, deep cold also affects people's ability to respond to emergencies. If something goes wrong, response time matters. In deep cold, response time slows. Putting on gear takes longer. Moving quickly is harder. Fine motor skills are reduced. Communication can be harder if devices are cold. Visibility may be limited by frost or blowing snow. So even a well-trained team may respond more slowly than they would in warmer conditions. This increases risk. Now, deep cold also increases the cost of safety. Safety systems require more gear, more spare clothing, more shelter options, more heating capacity, more fuel, more medical supplies, more backup power. All of that adds weight and volume. Weight and volume make access harder. So deep cold feeds into the access problem again. The colder the region, the more equipment is needed to operate safely, and the harder it becomes to transport that equipment. This is one of the reasons some inland Arctic regions remain less studied than coastal areas. Inland regions can be colder, with fewer access routes and fewer emergency options. Now there is another deep cold effect that is easy to overlook: sound and movement. In extreme cold, the environment can feel sharper. Footsteps crunch differently. Materials creak. Ice cracks loudly. Wind noise can be constant. This sensory intensity can increase stress over time. It can make rest harder. It can make people more alert, but also more exhausted. Now, none of this means scientists cannot work in deep cold. They do, and they have done it for decades. But it explains why certain areas remain avoided or rarely visited. A mission in deep cold requires more support. It requires more fuel. It requires more redundancy. It requires more time for simple tasks. It requires more safety margin. In some areas, the support needed becomes too heavy, too expensive, or too risky to justify. So deep cold becomes a gatekeeper. It limits where long-term camps can be placed. It limits how far teams can travel. It limits what equipment can survive. It limits how long people can stay functional. And it does so quietly, without drama. The cold doesn't have to cause an accident to end a mission. It can simply slow everything down until the schedule collapses, or break enough small components that the work becomes impossible. This is why deep cold is not just part of the Arctic background. In some regions, it is the defining factor. Now, as difficult as deep cold is, it is still a physical challenge that can be measured and planned for. There is another kind of barrier that is harder to measure: politics, borders, military interest, legal restrictions, permits. Some Arctic areas are avoided not because of weather or ice, but because of what humans have placed on top of the map. So next, the focus shifts to the invisible lines and restricted zones of the far north, and why some Arctic regions remain difficult to study because access is controlled as much by governments as by nature. Some parts of the Arctic feel quiet in a way that is different from normal wilderness. Not the calm quiet of snow-absorbing sound. Not the wide-open quiet of a place with few people. This is a different kind of quiet. It is the quiet of a place that stays empty on purpose. In the Arctic, There are regions where the lack of activity is not only because of distance, cold, or danger, it is because access is limited by human decisions. Borders, military interests, protected zones, and restricted areas shape where scientists can go and what they can do when they get there. This is one of the reasons certain Arctic areas remain avoided, even when the weather is manageable and the terrain is physically reachable. The Arctic is not just an environment, it is also a region of strategic value. It contains shipping routes that are becoming more usable as sea ice changes. It contains oil, gas, and mineral resources. It contains fisheries. It contains territory. It contains national security interests. It contains infrastructure that governments do not want disturbed or observed too closely. So some areas feel quiet because they are controlled. In the modern Arctic, the challenge is not only surviving nature, it is also navigating regulations, permits, and geopolitical realities. For scientists, this can become a barrier that is just as strong as the ice. The first and most obvious issue is national borders. The Arctic includes territory belonging to several countries. Each country has its own laws, research permitting processes, environmental rules, and security concerns. Even when scientists are acting purely for research, they still need permission to operate. They may need visas. They may need permits to travel. They may need permits to collect samples. They may need permits to fly drones. They may need permits to operate radio equipment. They may need to report their movements and plans. These requirements vary widely depending on location. In some regions, research access is relatively straightforward if you follow the rules. In other regions, access can be slow, complicated, or restricted. This can shape where research happens simply because it shapes how long planning takes and how uncertain approval becomes. Then there are restricted zones. Restricted zones can exist for many reasons. Military bases, radar stations, air defense systems, missile testing areas, sensitive communication infrastructure, strategic ports, border security. Some restricted zones are clearly marked. Some are not obvious unless you already know. Some restrictions apply only to certain activities. Some apply to certain seasons. Some apply to certain types of equipment. For example, a region might be open for travel but restricted for aerial surveys. It might be open for oceanographic sampling, but restricted for installing certain instruments. It might be open for local operations but restricted for foreign teams. These limitations can make research difficult. A team might be able to reach a site physically but not legally. Or they might be allowed to visit but not allowed to bring the equipment needed to do meaningful work. So the site remains quiet, not because no one wants to study it, but because the rules make it hard. Another barrier is airspace control. A lot of Arctic research relies on aircraft. Planes and helicopters are essential for access, mapping, and survey work. But airspace in some regions is tightly controlled. Flight permissions may be required. Flight paths may be restricted. Certain altitudes may be prohibited. Some areas may be closed entirely for security reasons. If a research project depends on flights, and flights are restricted, the project may not happen. This is one reason certain areas remain less mapped and less sampled. Without aerial support, the cost and difficulty increase sharply. Then there is the ocean. Arctic Ocean research often requires ships, but ships must follow national regulations, and in some regions there are restrictions on navigation routes, port access, and operational zones. In some places, icebreaker support may be required, and icebreaker support is often controlled by governments. That means access can depend on political decisions and scheduling priorities. If a research team cannot secure icebreaker support, they may not be able to reach the region at all. So the ocean can feel quiet for political reasons as much as environmental ones. Now there's another layer, protected areas. The Arctic contains national parks, wildlife reserves, and protected marine zones. These protections exist for good reasons. Arctic ecosystems are fragile. Disturbance can have long-lasting effects. Some species are threatened or sensitive. But protection also limits research. Some areas restrict sampling. Some restrict vehicle use. Some restrict camping, some restrict flights, some restrict the use of certain chemicals or equipment, some restrict access during breeding seasons. These restrictions can make it harder to study the very areas that are most ecologically important. Scientists can often work in protected areas with the right permits and protocols, but the process can be slow and strict. Some projects may be rejected if the impact is too high, so protected areas can become quiet zones in terms of human activity. This is not avoidance out of fear, it is avoidance out of responsibility and regulation. Now, there is also the reality of indigenous land rights and community control. Large parts of the Arctic are home to indigenous peoples who have lived there for thousands of years. Their knowledge of the land is deep, their relationship to the environment is direct, their communities are affected by research, by development, and by climate change. Ethical research requires partnership and respect. In many regions, scientists need permission and collaboration with local communities. They need to share plans, explain goals, and ensure that research benefits are not one-sided. This is not a barrier in the sense of hostility. It is a necessary part of responsible work. But it does affect where research happens and how quickly it can happen. A project cannot simply arrive and operate without engagement. That engagement takes time, trust, and ongoing communication. Some teams do this well and build long-term partnerships, others struggle. If a region has a history of extractive research, where outsiders collected data without returning benefits, communities may be cautious. That caution can slow new projects. So some areas remain quiet because they are guarded by experience. Now, beyond legal restrictions, there is also the issue of perception. Some Arctic regions are sensitive because of what they contain. Natural resources, oil and gas fields, mineral deposits, rare earth elements, strategic shipping lanes. In these regions, governments and companies may have strong interests. They may control access. They may limit what can be documented. They may restrict photography. They may restrict mapping. They may restrict public reporting of certain details. This is not always explicit, but it can influence what research is funded and what is allowed. Scientists might avoid areas where their work could be interpreted as surveillance or interference. They might avoid areas where permits are unpredictable. They might avoid areas where access depends on political relationships. This is another reason quiet zones exist. Now, there is also the issue of military activity itself. The Arctic is used for training, patrols, and strategic positioning. Some regions have active military infrastructure. Some have radar systems designed to detect aircraft and missiles. Some have submarine routes under ice. In such areas, the presence of civilian research teams can be seen as a complication. Even if a team has no interest in military matters, the overlap can create restrictions. So scientists may focus on areas with fewer security concerns simply because it is easier. Now, it is important to be clear about something. This does not mean the Arctic is full of secret bases and hidden operations everywhere. It means that certain regions have restrictions that are not obvious to outsiders. And those restrictions shape the map of research. They create blank spots not because the environment is impossible, but because access is limited. Now, the quietness of these places also has a psychological effect. A remote area that is quiet because it is empty feels one way. A remote area that is quiet because it is restricted feels different. There is a sense of boundaries. Not physical boundaries like fences, but invisible ones. A team may know they cannot travel beyond a certain line. They may know they cannot fly over a certain area. They may know they cannot deploy instruments in certain waters. This changes how research is designed. It can force scientists to work around restricted zones, which can create gaps in data. It can limit long transects and continuous measurements. It can create blind spots in mapping and sampling. And because Arctic systems are interconnected, gaps matter. If you cannot measure one region, it becomes harder to understand the flow of heat, water and ice through the larger system. So restricted zones can have scientific consequences far beyond their borders. Now, there is another reason some places stay quiet, and it is not about law or military activity. It is about risk and liability. In remote environments, accidents can become major incidents. Governments and institutions may be cautious about allowing operations in areas where rescue is difficult. Permitting agencies may require detailed safety plans. Insurance requirements may be strict. Some projects may not meet the threshold. This is not censorship, it is risk management. But it still affects access. So a region can be physically reachable and still remain quiet because the administrative burden is too high. Now, when scientists choose where to work, they are balancing many factors at once: scientific value, safety, cost, access, permits, time, equipment needs, team size. If a site is restricted or complicated politically, it has to offer enough scientific value to justify the extra effort. Sometimes it does, and teams push through the process. Sometimes it doesn't, and teams choose another site. Over time, this creates patterns. Some areas become hubs of research, others remain sparse, and the sparse areas can feel quiet for a reason that has nothing to do with weather or ice. Now, there is also a subtle effect. In some regions, data exists but is not shared widely. Some research may be conducted by government agencies or military-linked programs and not released publicly. Some data may be classified, some may be restricted, some may be available only through limited channels. This can create the impression of a blank spot even when measurements have been made. From the outside, it looks like no one has studied the area. In reality, information may exist, but not be accessible. This matters because science advances through open data and peer review. When data is limited, understanding develops more slowly. So quiet zones are not only physical, they can be informational. Now this connects to the larger theme of why scientists avoid certain Arctic areas. Avoidance is not always about fear. It is often about constraints. Nature constrains with weather, ice, and cold. Humans constrain with borders, permits, and restricted zones. In some regions, both sets of constraints overlap. Those regions become the hardest to study. They're remote, unstable, and controlled. So they stay quiet. And that quietness shapes what the world knows about the Arctic. Now, after considering all of these barriers, there is still one more reason certain areas remain avoided, and it is one that ties together almost everything discussed so far. Money. Not just funding in general, but the specific economics of Arctic research. The cost of ships, aircraft, fuel, equipment, safety systems, and time. Even when a region is scientifically important, it may be too expensive to study regularly. So next, the focus shifts to the financial reality behind Arctic exploration, and why the blank spots on the map often exist not because humans lack curiosity, but because curiosity has a price. The Arctic is one of the most studied remote regions on Earth, and it is still full of gaps. That sounds like a contradiction, but it isn't. The Arctic has satellites watching it every day. It has research stations in multiple countries. It has ships crossing its seas. It has aircraft mapping its coastlines. It has sensors drifting through its waters. It has scientists measuring ice thickness, air temperature, ocean salinity, and wildlife patterns. And yet, there are still places where the data is thin. There are still seasons where measurements are rare. There are still processes that are understood in broad outlines but not in detail. There are still changes happening faster than the observing systems can keep up with. This matters because the Arctic is not isolated. What happens there affects weather farther south. It affects sea level. It affects ocean circulation. It affects ecosystems. It affects economies. It affects infrastructure. It affects global climate feedbacks. So the things we still don't know are not just academic. They shape decisions people make in the real world. And the reason we still don't know them comes back to everything already discussed. The Arctic is difficult to access, difficult to operate in, and difficult to measure continuously in the most challenging regions. That creates blind spots. Those blind spots are not empty out of neglect. They are empty because they're expensive, risky, and logistically complicated to fill. The first category of what we still don't know is the basic question of how fast certain parts of the Arctic are changing, and exactly how. People hear about Arctic warming and sea ice decline, but the details matter. Sea ice extent is tracked well from satellites, but sea ice thickness is hard to measure. Satellites can estimate thickness, but direct measurements are limited. Thickness varies widely across regions, and thickness determines how resilient ice is to melting and breaking. In some areas, thickness data is sparse because the ice is unstable and hard to reach. Those are often the areas where the biggest changes are happening. This matters because thinner ice behaves differently. It breaks more easily, it drifts faster, it melts faster, it allows more open water. More open water absorbs more heat. More heat accelerates change. So understanding thickness changes is essential for predicting future ice conditions. Another major unknown is the detailed behaviour of the marginal ice zone. This is the shifting boundary where sea ice meets open water. It is a region of constant change, driven by wind, waves, ocean heat, and seasonal cycles. It is also one of the most important regions for climate feedbacks. Waves break up ice into smaller pieces. Smaller pieces melt faster. Open water absorbs more sunlight. Storms mix heat into the upper ocean. Heat melts more ice. These processes happen on scales that are difficult to measure continuously. Ships can study parts of the ice edge, but ships are limited by ice conditions and cost. Aircraft can map large areas, but flights depend on weather and permissions. Satellites can see surface patterns, but they cannot capture every detail of wave action and mixing. So the marginal ice zone remains one of the biggest gaps, and it matters because it influences how quickly sea ice can retreat and how long it can recover. Another unknown involves ocean circulation in the Arctic. The Arctic Ocean is not a simple basin of cold water. It has layers of different salinity and temperature. It has inflows from the Atlantic and Pacific. It has freshwater input from rivers. It has mixing driven by storms, tides, and ice movement. These processes determine how heat is distributed under the ice. If warm water moves upward, it can melt ice from below. If freshwater layers strengthen stratification, they can limit mixing. If storms increase mixing, they can bring heat to the surface. Understanding these details is critical for predicting ice stability, but measuring them is hard. Instruments can be deployed under ice, but retrieval is difficult. Autonomous vehicles can collect data, but they can be lost. Ships can measure water properties, but only in accessible seasons and routes. So the Arctic Ocean still contains gaps in understanding, especially in remote regions far from shipping lanes. Another unknown is the behaviour of permafrost. Permafrost is frozen ground, but it is not uniformly frozen. It contains ice, organic material and soil in different mixtures. When it warms, it can thaw unevenly. Thawing permafrost can release greenhouse gases like carbon dioxide and methane as organic material decomposes. It can also destabilise land, causing ground collapse, erosion and infrastructure damage. Scientists know permafrost is warming, but the details of how fast and how much carbon will be released are still uncertain. This uncertainty matters because permafrost carbon feedback could accelerate climate change. Measuring permafrost is difficult because it varies over small distances. It requires ground-based monitoring. It requires long-term stations. It requires repeated sampling. In remote regions, those stations are hard to maintain. So permafrost remains a major unknown. Another unknown is the behaviour of Arctic clouds. Clouds are one of the biggest sources of uncertainty in climate models worldwide, and the Arctic is especially challenging. Clouds can warm the surface by trapping heat. They can cool the surface by reflecting sunlight. Their net effect depends on altitude, thickness, particle composition, and season. Arctic clouds often persist for long periods and behave differently than clouds in lower latitudes. They can form in conditions that models struggle to simulate accurately. This matters because clouds influence the energy balance of the region. If models misrepresent clouds, they misrepresent temperature trends and ice melt trends. Measuring clouds requires aircraft, balloons, and ground-based instruments. Those tools are limited in remote areas, so cloud behavior remains an uncertainty. Another major unknown is the role of storms. Storms influence sea ice movement, ice breakup, ocean mixing, and heat transport. The Arctic is seeing changes in storm patterns, but the details are still being studied. Do storms become more frequent, more intense? Do they track differently? Do they occur in different seasons? These questions matter because storms can accelerate ice loss by breaking up ice and exposing open water. Storms also affect coastal erosion, which is already increasing in many Arctic communities. Measuring storms is easier than measuring some other processes, but storm impacts on ice and ocean require field observations that are hard to collect in the most dynamic regions. So storm effects remain uncertain. Another unknown is ecosystem change. Arctic ecosystems are shifting. Species ranges are moving. Some animals are struggling. Some are adapting. New species are moving north as waters warm. Marine ecosystems are especially complex. Plankton communities change with temperature and light. Fish distributions shift. Predators follow prey. Ice-associated species lose habitat. These changes matter not only for wildlife, but for fisheries and food security. Measuring ecosystem change requires repeated surveys and long-term monitoring. That is difficult in remote regions, so ecological knowledge is uneven. Another unknown is the stability of glaciers and ice sheets in the Arctic region, especially Greenland. Greenland's ice sheet is a major contributor to sea level rise. Scientists measure its mass loss using satellites and field studies, but predicting future behavior is still complex. Ice sheet dynamics involve surface melting, meltwater flow, basal lubrication, and glacier calving. These processes can accelerate or slow depending on conditions. Understanding them requires detailed measurements in harsh environments, often near calving fronts and crevassed zones. Those areas are dangerous and difficult to access, so there are still uncertainties in how quickly Greenland will lose ice under different warming scenarios. Now, these unknowns matter because they feed into models. Climate models are tools for projecting future conditions. They rely on physics, data, and assumptions. When data is missing, uncertainty increases. Uncertainty does not mean ignorance. It means a wider range of possible outcomes. In climate planning, a wider range of outcomes makes decisions harder. Infrastructure planning in northern regions depends on permafrost stability. Shipping depends on ice conditions. Fisheries depend on ecosystem shifts. Coastal communities depend on erosion and storm patterns, so the unknowns affect real planning. They also affect global systems. The Arctic influences the jet stream and weather patterns in the mid-latitudes. It influences ocean circulation, including the movement of heat in the Atlantic. It influences global albedo, the reflectivity of the planet. So Arctic change is not local, it is connected. That is why filling the blank spots matters. Now it is important to understand that unknown does not mean unstudied. Many processes are studied, but the Arctic is large and it changes quickly. Some measurements are seasonal, some are limited in space, some are limited by cost. A satellite can tell you ice extent daily, but not ice thickness everywhere. A ship can measure ocean conditions along a route, but not in every basin. A station can measure permafrost at one point, but not across an entire region. So the Arctic is observed, but unevenly. That unevenness is the reason certain questions remain open. Now, there is also a deeper reason why the unknowns matter. They shape risk. If you do not know how quickly ice will thin in a region, shipping companies cannot plan reliably. If you do not know how permafrost will behave, engineers cannot design foundations confidently. If you do not know how storm patterns will shift, coastal defences become harder to plan. So unknowns translate into risk and cost. That is why Arctic research is not just curiosity. It is preparation. It is trying to reduce uncertainty in a region that is changing fast. Now, the blank spots remain partly because the Arctic resists continuous observation. In the hardest regions, instruments fail, access is limited, ice moves, weather changes, darkness limits operations, wildlife adds risk, political restrictions limit routes, costs rise. So the places that are most difficult are often the places where uncertainty remains highest. This is not because scientists are ignoring them. It is because the Arctic selects against easy observation. But the effort continues. Autonomous sensors are improving. Satellite systems are expanding. International collaborations are building shared data sets. New icebreaker missions are planned. Drones and remote systems are becoming more capable. So the unknowns are shrinking, but they are not gone. And even as we learn more, new questions appear, because the system itself is changing. That is why the Arctic remains one of the most important research frontiers on Earth. Not because it is exotic, but because it is influential. Now, after exploring what we still don't know, the story naturally moves to the last practical reality that shapes everything. Cost. Not just money in a general sense, but the specific cost of reaching remote areas, staying safe, keeping technology working, and collecting data long enough to matter. Because in the Arctic, knowledge is not only earned with curiosity, it is earned with logistics, fuel, equipment, and time. So next, the focus shifts to the price of Arctic science, and why some blank spots remain, not because humans lack the tools to reach them, but because the cost of doing it repeatedly is still enormous. And that's the part that stays with you. Not the dramatic images people like to use when they talk about the Arctic, but the simple reality that there are still places where knowledge is slow, expensive, and hard-earned. After everything we've covered, it becomes clear why certain areas remain lightly studied even now. It's not because scientists are ignoring them. It's not because they ran out of curiosity. It's because the Arctic has a way of turning curiosity into a logistical problem, then turning that logistical problem into a safety problem, and then turning the safety problem into a cost problem that can't be ignored. In some regions, the weather alone is enough to stop a mission from functioning the way it was designed to. Forecasts carry more uncertainty, storms can stall, fog can sit in place for days, and wind can erase visibility without warning. A team can arrive with a plan and still spend most of the week waiting for conditions that never settle long enough to work. Then there's the ice, and the fact that it isn't a stable platform in the way most people imagine. It moves, it fractures, it compresses into ridges, it opens into leads, it refreezes into thin surfaces that look safe until they fail. Snow hides the weak spots, currents melt from below. Even when the surface looks calm, the structure underneath can be changing. Distance makes all of this heavier. If you're close to infrastructure, you can tolerate more uncertainty. You can wait out bad weather. You can fix a broken part. You can change the plan and still get something done. But in the farthest zones, distance turns every problem into a bigger one. Fuel becomes a limit. Weight becomes a limit. Time becomes a limit. Communication becomes a limit. Rescue becomes a question mark. When a region is remote enough, the margin for error shrinks until it's almost gone. Technology helps, but it doesn't solve everything. Batteries still drain fast in cold, connectors still ice up, sensors still drift, plastic still cracks, lubricants still thicken, data still gets lost quietly when something fails, and nobody finds out until months later. In a place where you can't just send someone back the next day, one failure can erase an entire season of work. Even navigation and communication have their own Arctic complications. The magnetic environment behaves differently near the pole. Space weather can disturb signals. Compasses become less dependable. GPS can degrade when the upper atmosphere becomes more active. None of this is constant chaos, but it adds uncertainty to an environment that already has plenty. Then there's the human factor, which is always there, even when people try to pretend it isn't. Polar night and polar day change how the brain keeps time. Sleep gets disrupted. fatigue builds, attention slips, motivation can drop. In the dark, the world shrinks into a narrow circle of headlamp light. In constant daylight, it becomes easy to work too long and rest too little. Either way, the body and the mind have to work harder just to stay balanced. Wildlife adds another layer that cannot be negotiated with. Polar bears don't need to warn you. They don't need to announce themselves. They can approach quietly, they can return, and they can turn a normal day into a serious emergency. Even smaller animals can cause problems by damaging equipment or getting into supplies. In the most remote areas, a wildlife incident is not a story you tell later. It can become the reason the mission ends early, and some places are quiet for reasons that have nothing to do with nature. Borders, permits, protected zones, restricted areas, controlled airspace. There are parts of the Arctic where access is shaped by human decisions as much as ice and weather. Some regions can be reached physically, but not easily studied, not easily mapped, not easily worked in with the tools researchers need. All of this explains the blank spots, not as mysteries, but as gaps created by real constraints. It also explains why those gaps matter, because the Arctic isn't separate from the rest of the world. The changes there influence ocean circulation, sea level, weather patterns, ecosystems, and long-term climate behaviour. When there are regions where the data is thin, it widens uncertainty. When uncertainty widens, planning becomes harder, and risk becomes harder to manage. Still, the direction is clear. The Arctic is being watched more closely than ever. Satellite systems improve, autonomous instruments get better, collaboration grows, more missions push farther and stay longer. Some of the blank spaces are shrinking slowly but steadily as technology and planning improve. But even with all of that, some places remain difficult enough that they still resist routine study, not because they are impossible, because they are expensive to return to again and again, and science depends on returning again and again. That's the difference between a single trip and real understanding. A single trip can capture a moment. Real understanding comes from repetition, from long records, from measurements that survive long enough to show what is changing and how fast. So the Arctic keeps some of its secrets. For now. Not because it is hiding them, but because it demands a price for access that not every mission can pay. And it demands a level of stability that some regions simply don't offer. And if you're listening to this as you settle down, let that idea sit in the background without making it heavy. The Arctic is vast, but it doesn't have to feel threatening. It can just be a reminder that there are still places on Earth where nature sets the terms, where patience matters, where preparation matters, and where not everything can be forced into a schedule. Thank you for spending this time here with me. If you enjoyed this kind of calm science storytelling, you can like the video, subscribe to the channel, and join us again next time. For now, you can let your attention drift away from the ice and the wind and the long distances, and let the world go quiet for a while.